Hey, been enjoying the music for almost 6 minutes. I was hanging out with my dog outside. Yay, I can't see right now. My eyes aren't adjusted. Well, I mean, I can. It's just weird. You know, you know. I'm sure you all understand, right? Yeah. Oh, hi, Bella. Ah, let's scoot in. Oh, yes. He's outside. And you want to say hi. Ugh. Yeah, I was not feeling like streaming yesterday, and I was considering not today. But I was like, I don't have much else to do. I'd be rather bored. I think. Well, I do have stuff to do, but I don't want to do them. They're not as necessary as this. That was before my Adderall kicked in. So, yeah. Celebrate. Huh. Interessante. Alright. 2D navigation overview. Godot provides multiple objects, classes, and servers to facilitate grid-based or mesh-based navigation and pathfinding for 2D and 3D games. The following section provides a quick overview over all available navigation-related objects in Godot for 2D scenes and their primary use. Godot provides the following objects and classes for 2D navigation. A-star 2D. A-star 2D objects provide an option to find the shortest path in a graph of weighted points. The A-star 2D class is best suited for cell-based 2D gameplay that does not require actors to reach any possible position within an area, but only predefined distinct positions. A-star Grid 2D. A-star Grid 2D is a variant of A-star 2D that is specialized for partial 2D grids. A-star 2D is simpler than simpler to use when applicable because it doesn't require you to manually create points and connect them together. Navigate Server 2D. Navigate Server 2D provides a powerful server API to find shortest path between two positions on an area defined by a navigation mesh. The navigation server is best suited for 2D real-time gameplay that does require the actors to reach any possible position within a navigation mesh defined area. Mesh-based navigation scales well with large game worlds, and as a large area can often be defined with a single polygon, when it would require many grid cells. The navigation server holds different navigation maps, each consists of regions that hold navigation mesh data. Agents can be placed on a map for avoidance calculation. RIDs are used to reference internal maps, regions, and agents when commuting with the server. The following navigation RID types are available. Nav map RID, reference to a specific navigation map that holds regions and agents. The map will attempt to join the navigation meshes of the regions by proximity. The map will synchronize regions and agents each physics frame. Nav region RID. Reference to specific navigation region that can hold navigation mesh data. The region can be enabled or disabled, or the use restricted with a navigation layer bitmask. Navlink RID. Reference to a specific navigation link that connects two navigation mesh positions over arbitrary distances. Nav agent RID. Reference to a specific avoidant agent. The avoidant is specified by a radius value. Nav obstacle RID. Reference to a specific avoidance obstacle used to affect and constrain the avoidance velocity of agents. Give me a second, I gotta do a thing. There we go. Alright, let's pull it back on over. Following scene tree nodes are available as helpers to work with Navigation Server 2D API. Navigation Region 2D Node. A node that holds a navigation polygon resource that defines a navigation mesh for the navigation server 2D. The region can be enabled or disabled. The use in pathfinding can be further restricted through the navigation layer's bit mask. The navigation server 2D will join the navigation meshes of regions by proximity for a combined navigation mesh. Navigation Link 2D Node. A node that connects two positions on navigation meshes over arbitrary distances for pathfinding. The link can be enabled or disabled. The link can be made one-way or bidirectional. The use in pathfinding can be further restricted through the navigation layer's bit mask. Links tell the pathfinding that a connection exists and at what cost. The actual agent handling the movement needs to happen in custom scripts. Navigation Agent 2D Node, a helper node used to facilitate common navigation server 2D API calls for pathfinding and avoidance. Use this node with a 2D node 2D inheriting parent node. Shelby? Was that Bella? That's Bella. I didn't know. Navigation Obstacle 2D Node, a node that can be used to affect and constrain the avoidance velocity of avoidance enabled objects. This node does not affect the pathfinding of agents. You need to change the navigation meshes for that instead. The 2D navigation meshes are defined with the following resources. Navigation Polygon Resource. A resource that holds 2D navigation with mesh data. It provides polygon drawing tools to allow defining navigation areas inside the editor as well as at runtime. The Navigation Region 2D node uses this resource to define its navigation area. The Navigation Server 2D uses this resource to update the navigation mesh of individual regions. The tileset editor creates and uses this resource internally when defining the tile navigation areas. See also, you can see how 2D navigation works in action using the 2D navigation polygon in grid-based navigation with A-Star Grid 2D demo projects. Bleh. Setup for 2D scene. The following steps show a basic setup for minimal viable navigation in 2D. It uses the Navigation Server 2D and a Navigation Agent 2D for path movement. Add a Navigation Region 2D node to the scene. Click on the region node and add a new navigation polygon resource to the region node. Holy there's a lot in navigation. 3. Define movable navigation area with the navigation polygon draw tool. Then click the Bake Navigation Polygon button on the toolbar. Note, the navigation mesh defines the area where an actor can stand and move with its center. Leave enough margin between the navigation polygon edges and collision objects to not get path-following actors repeatedly stuck on collisions. 4. Add Character Body 2D node in the scene with a basic collision shape and a sprite or mesh for visuals. Add a Navigation Agent 2D node below the Character node. Add the following script to the Character Body 2D node. We can make sure to set a movement target after the scene has fully loaded and the navigation server had time to sync. Note, on the first frame of the navigation server map has not synchronized region data and any path query will return empty. Wait for the navigation server synchronization by waiting one frame in the script. Water. Boom, boom, boom. 3D Navigation Overview. Godot provides multiple objects, classes, and servers to facilitate grid-based or mesh-based navigation and pathfinding for 2D and 3D games. The following section provides a quick overview over all available navigation-related objects in Godot for 3D scenes and their primary use. Godot provides the following objects and classes for 3D navigation. A-Star 3D. Objects provide an option to find the shortest path in a graph of void points. The A-Star 3D class is best suited for cell-based 3D gameplay that does not require actors to reach any possible position within an area, but only predefined distinct positions. Navigations... Wait, this is for 3D shit. Boop. Using Navigation Server. 2D and 3D version of Navigation Server are available as Navigation Server 2D and Navigation Server 3D respectively. Communicating with the Navigation Server. To work with the Navigation Server means to prepare parameters for a query that can be sent to the Navigation Server for updates or requesting data. To reference the internal Navigation Server objects like maps, regions, and agents, RIDs are used as identification numbers. Every navigation-related node in the scene tree has a function that returns the RID for this node. Threading and synchronization. The navigation server does not update every change immediately, but awaits until the end of the physics frame to synchronize all the changes together. Waiting for synchronization is required to apply changes to all maps, regions, and agents. Synchronization is done because some updates, like recalculation of the entire navigation map, are very expensive and require updated data from all other objects. Also, the navigation server uses a thread pool by default for some functionality, like avoidance calculation between agents. Waiting is not required for most get functions that only request data from the navigation server without making changes. Note that not all data will account for changes made in the same frame. Example, if an avoidance agent changed the navigation map this frame, the agent get map function will still return the old map before the synchronization. The exception to this are nodes that store their values internally before sending the update to the navigation server. When a getter on a node is used for a value that was updated in the same frame, it will return that already updated value stored on the node. The navigation server is thread safe as it places all API calls that want to make changes in a queue to be executed in a synchronization phase. Synchronization for the navigation server happens in the middle of the physics frame after scene input from scripts and nodes are all done. God, my nose is stuffy. So, to remedy this issue, I'm gonna take some allergy relief. Hopefully that should help. Are there two of you? Or is it... Huh. Interesting. There's somebody else here. Hi. Yeah, hi. I'm just learning Godot, and then after I go through all of this, I'm gonna make a game. Good game, hopefully. JRPG should be fun. Yeah. I don't know why you're here, but yeah. Maybe you're just along for the ride or something. I don't know. Threading and synchronization. The navigation server does not update every change immediately, but wait, I already read all that, didn't I? No, the important takeaway is that most navigation server changes take effect after the next physics frame and not immediately. This includes all changes made by navigation-related nodes in the scene tree or through scripts. Note, all setters and delete functions require synchronization. 2D and 3D navigation server differences. Navigation server 2D and navigation server 3D are equivalent in functionality for the dimension. Technically, it is possible to use the tools for creating navigation meshes in one dimension for the other dimension. Example, baking a 2D navigation mesh with the 3D navigation mesh when using flat 3D source geometry, or creating 3D flat navigation meshes with the polygon outline draw tools of navigation region 2D and navigation polygons. Waiting for synchronization. At the start of the game, a new scene or procedural navigation changes any path query to a navigation server will return empty or wrong. The navigation map is still empty or not updated at this point. All nodes from the scene tree need to first upload their navigation-related data to the navigation server. Each added or changed map region or agent need to be registered with the navigation server. Afterward, the navigation server requires a physics frame for synchronization to update the maps, regions, and agents. One workaround is to make a diff is to make a deferred call to a custom setup function, so all nodes are ready. This setup function makes all the navigation changes, example, adding procedural stuff. Afterwards, the function waits for the next physics frame before continuing with path queries. Server avoidance callbacks. If RVO avoidance agents are registered for avoidance callbacks in the navigation server dispatches, their velocity computed signals just before the physics server synchronization. To learn more about navigation agents, see using navigation agents. The simplified order of execution for navigation agents that use avoidance. Physics frame starts. Physics process delta. Velocity property is set on navigation agent node. Agent sends velocity and position to navigation server. Navigation server waits for synchronization. Navigation server synchronizes and computes avoidance velocities for all registered avoidance agents. Navigation server sends safe velocity vector with signals for each registered avoidance agents. Agents receive the signal and move their parents. Example, with move inside or linear velocity. Physics server synchronizes. Physics frame ends. Therefore, moving a physics body actor in the callback function with the safe velocity is perfectly thread and physics safe, as all happens inside the same physics frame before the physics server commits to changes and does its own calculations. Using navigation maps. That's a silly example. A navigation map is an abstract navigation world on the navigation server identified by the navigation server RID. A map can hold and connect a near infinite number of navigation regions with navigation meshes to build the traversable areas of a game world for pathfinding. A map can contain avoidance agents. Collision avoidance will be calculated based on the agents present in the map. Note, different navigation maps are completely isolated from each other, but navigation regions and avoidance agents can be switched between different maps. Switches will become effective on navigation server synchronization. Default navigation maps. Don't go scrolling up and down anymore. By default, Godot creates a navigation map for World 2D and World 3D of the root viewport. The 2D default navigation map RID can be obtained with getWorld2D.getNavigationMap from any Node 2D inheriting node. The 3D default navigation map RID can be attained using that from any Node 3D inheriting node. Yeah, I'm also just skipping over all 3D shit, because I'm not going to be using that here in my game, so I don't need to worry about learning it, at least right now, unless in the future I for some reason want to make a 3D game, which I don't want to. But we'll see. We'll see what the future holds. Creating new navigation maps. The navigation server can create and support as many navigation maps as required for specific gameplay. Additional navigation maps are created and handled by using the navigation server API directly. Example, to support different avoidance agent or actor locomotion types. For example, uses of different navigation maps see support different actor types and support different actor locomotion. Each navigation map individually synchronizes queued changes to its navigation regions and avoidance agents. A navigation map that has not received changes will consume little to no processing time. Navigation regions and avoidance agents can only be part of a single navigation map, but they can switch map at any time. A navigation map switch will take effect only after the next navigation server synchronization. Note, there is no difference between navigation maps created with the Navigation Server 2D API or the Navigation Server 3D API. Using navigation regions. Navigation regions are the visual node representation of a region of the navigation map on the navigation server. That was a mouthful of a sentence. Each navigation region node holds a resource for the navigation mesh data. Both 2D and 3D versions are available as Navigation Region 2D and Navigation Region 3D respectively. Individual navigation regions upload their 2D navigation polygon and 3D navigation mesh resource data to the navigation server. The navigation server map turns this information into a combined navigation map for pathfinding. To create a navigation region using the scene tree Add a Navigation Region 2D or Navigation Region 3D node to a scene. All regions require a Navigation Mesh resource to function. See Using Navigation Meshes. To learn how to create and apply navigation meshes. Navigation regions will automatically push global transform changes to the region on the navigation server, which makes them suitable for moving platforms. The navigation server will attempt to connect the navigation meshes of individual regions. When they're close enough for more details, see Connecting Navigation Meshes. To connect navigation regions over arbitrary distances, see Using Navigation Links to learn how to create and use navigation links. Warning: while changing the transform of a navigation region node does update the region position on the navigation server. Changing the scale does not. A navigation mesh resource has no scale and needs to be fully updated when source geometry changes scale. Regions can be enabled or disabled, and if disabled, will not contribute to further pathfinding queries. Note: existing paths will not automatically update when a region gets enabled or disabled. Creating a new navigation regions. New navigation region nodes will automatically register to the default world navigation map for their 2D or 3D dimension. The region already can be obtained from navigation region nodes with getRid. New regions can also be created with the navigation server API and added to any existing map. If regions are created with the navigation server API directly, they need to be assigned a navigation map manually. Note: navigation regions can only be assigned to a single navigation map. If an existing region is assigned to a new navigation map, it will leave the old map. Hey, for the human in chat, or just watching, I want to know, is the audio good? Does it sound good? Is it loud enough? Is it too loud? Is it too quiet? I wanna know. No real time, anyway. That'd be fantastic if you could say. Because viewing experience is important. Using navigation meshes. 2D and 3D versions of the navigation mesh are available as navigation polygon and navigation mesh respectively. Note: navigation mesh only describes a traversable area for an agent's center position. Any radius values an agent may have are ignored. If you want pathfinding to account for agent's collision size, you need to shrink the navigation mesh accordingly. Navigation works independently from other engine parts like rendering or physics. Navigation meshes are the only things considered when doing pathfinding. Example: visuals and collision shapes are example of completely ignored by the navigation system. If you need to take other data, like visuals for example, into account when doing pathfinding, you need to adapt your navigation meshes accordingly. The process of factoring in navigation restrictions in navigation meshes is commonly referred to as navigation mesh baking. Navigation mesh describes a surface blah blah blah. If you experience clipping or collision problems while following navigation paths, always remember that you need to tell the navigation system that your intentions are through an appropriate navigation mesh. By itself, the navigation system will never know this is a tree or rock wall collision, shape, or visual mesh, because it only knows that here I was told I can path safely because it's on a navigation mesh. Navigation mesh baking can be done either by using a navigation region 2D or navigation region 3D, or by using navigation server 2D and navigation server 3D API directly. Baking a navigation mesh with a navigation region. Baking a navigation mesh with agent radius offset from geometry. The navigation mesh baking is made more accessible with the navigation region node. When baking into a navigation region node, the individual parsing, baking, and region update steps are all combined into one function. The nodes are available in 2D and 3D as navigation region 2D and navigation region 3D respectively. Tip: the navigation mesh source geometry mode can be switched to parse specific node group names, so nodes that should be baked can be placed anywhere in the scene. Baking with a navigation region 2D. When a navigation region 2D node is selected in the editor, bake options as well as polygon draw tools appear in the top bar of the editor. In order for the region to work, a navigation polygon resource needs to be added. The properties to parse and bake a navigation mesh are then part of the used resource and can be found in the resource inspector. The result of the source geometry parsing can be influenced with the following properties. The parsed geometry type that filters if visual objects or physics objects or both should be parsed from the scene tree. For more details on what objects are parsed and how, see the section about parsing source geometry below. Yes, sir, sir. The collision mask filters which physics collision objects are included when the parsed geometry type includes static colliders. The source geometry mode that defines on which nodes to start the parsing and how to traverse the scene tree. The source geometry group name is used when only a certain node group should be parsed. It depends on the selected source geometry mode. With the source geometry added, the result of the baking can be controlled with the following properties. The cell size sets the rasterization grid size and should match the navigation map size. The agent radius shrinks the baked navigation mesh to have enough margin for the agent collision size. The navigation region 2D baking can also be used at runtime with scripts. To quickly test the 2D baking with default settings, adding navigation region 2D, add a navigation polygon resource to the navigation region 2D, add a polygon 2D below the navigation region 2D, draw one navigation polygon outline with the selected navigation region 2D draw tool. Draw one polygon 2D outline inside the navigation polygon outline with the selected polygon 2D draw tool. Hit the editor bake button and a navigation mesh should appear. Baking a navigation mesh with the navigation server. The navigation server 2D and navigation server 3D have API functions to call each step of the navigation mesh baking process individually. Parse source geometry data can be used to parse source geometry to a reusable and serializable resource. Bake from source geometry data can be used to bake a navigation mesh from already parsed data, example to avoid runtime performance issues with redundant parsing. Bake from source geometry data async is the same but bakes the navigation mesh deferred with threads not blocking the main thread. Compared to navigation region, the navigation server offers finer control over the navigation mesh baking process. In turn, it's more complex to use but also provides more advanced options. Some other advantages of the navigation server or other navigation regions are the server can parse source geometry without baking, example to cache it for later use. The server allows selecting the root node at which to start the source geometry parsing manually. The server can accept and bake from procedurally generated source geometry data. The server can bake multiple navigation meshes in sequence while reusing the same source geometry data. To bake navigation meshes with the navigation server, source geometry is required. Source geometry is geometry data that should be considered in navigation mesh baking process. Both navigation meshes for 2D and 3D are created by baking them from source geometry. 2D and 3D versions of source geometry resources are available as shit. I lost where I was. I think I was there. Navigation mesh source geometry data 2D and navigation mesh source geometry data 3D respectively. I think I was here. Down here. I want to say that's where I was. Source geometry can be geometry parsed from visual message, from physics collisions or procedural created arrays of data, like outlines 2D and triangle faces 3D for convenience. Source geometry is commonly parsed directly from node setups in the scene tree. For runtime navigation mesh rebakes, be aware that the geometry parsing always happens on the main thread. Note, the scene tree is not thread safe. Parsing source geometry from the scene tree can only be done on the main thread. Warning, the data from the visual meshes and polygons needs to be received from the GPU. Stalling the rendering server in the process for runtime rebaking. Prefer using physics shapes as parsed source geometry. Source geometry is stored inside resources so the created geometry can be reused for multiple bakes. Example, baking multiple navigation meshes for different agent sizes from the source geometry. This also allows to save source geometry to disk so it can be loaded later. Example, to avoid the overhead of parsing it again at runtime. The geometry data should be in general kept very simple, as many edges are often required but as few as possible. Especially in 2D, duplicated and nested geometry should be avoided as it forces polygon hole calculation that can result in flipped polygons. An example for nested geometry would be a smaller static body 2D shape placed completely inside the bounds of another static body 2D shape. Baking navigation mesh chunks for large worlds. See also, you can see the navigation mesh chunk baking in process in the navigation mesh chunk 2D and navigation mesh chunks 3D demo projects. To avoid misaligned edges between different region chunks, the navigation meshes have two important properties for the navigation mesh baking process: the baking bounds and border size. Together, they can be used to ensure perfectly aligned edges between region chunks. Baking bound only, baking bound plus border size. The baking bound, which is an axis-aligned rect2 for 2D and AABB for 3D, limits the used source geometry by discarding all the geometry that is outside of the bounds. The navigation polygon properties, bake rect and bake direct offset, can be used to create and place the 2D baking bound. The navigation mesh properties, filter baking AABB and filter baking AABB offset, can be used to create and place the 3D baking bound. With only the baking bound set, another problem still exists. The resulting navigation mesh will inevitably be affected by necessary offsets, like the agent radius, which makes the edges not aligned properly. This is where the border size property for navigation mesh comes in. The border size is an inward margin from the baking bound. The important characteristic of the border size is that it is unaffected by most offsets and processing, like the agent radius. Instead of discarding source geometry, the border size discards parts of the final surface of the baked navigation mesh. If the baking bound is large enough, the border size can remove the problematic surface parts so that the only intended chunk size is left. Note, the baking bounds need to be large enough to include a reasonable amount of source geometry from all the neighboring chunks. Warning, in 3D, the functionality of the border size is limited to the XZ axis. Navigation mesh baking common problems. There are some common user problems and important caveats to consider when creating or baking navigation meshes. Navigation mesh baking creates frame rate problems at runtime. The navigation mesh baking is by default done on a background thread, so as long as the platform supports threads, the actual baking is rarely the source of any performance issues, assuming a reasonably sized and complex geometry for runtime rebakes. The common source for performance issues at runtime is the parsing step for source geometry that involves nodes and the scene tree. The scene tree is not thread safe, so all the nodes need to be parsed on the main thread. Some nodes with a lot of data can be very heavy and slow to parse at runtime. Example, a tile map has one or more polygons for every single used cell and tile map layer to parse. Nodes that hold meshes need to request the data from the rendering server, stalling the rendering in the process. To improve performance, use more optimized shapes. Example, collision shapes over detailed visual meshes, and merge and simplify as much geometry as possible up front. If nothing happens, don't parse the scene tree and add the source geometry procedural with scripts. If only pure data arrays are used as source geometry, the entire baking process can be done on a background thread. Navigation mesh creates unintended holes in 2D. Navigation mesh baking in 2D is done by doing polygon clipping operations based on outline paths. Polygons with holes are a necessary evil to create more complex 2D polygons that can become unpredictable for users with many complex shapes involved. To avoid any unexpected problems with polygon hole calculations, avoid nesting any outlines inside other outlines of the same type, traversable or obstruction. This includes the parsed shapes from nodes. Example, placing a smaller static body 2D shape inside a larger static body 2D shape can result in the resulting polygon being flipped. Navigation mesh appears inside geometry in 3D. The navigation mesh baking in 3D has no concept of inside. The voxel cells used to rasterize the geometry are either occupied or not, removing the geometry that is on the ground inside the other geometry if that is not possible, and add smaller dummy geometry inside with as few triangles as possible so the cells are occupied with something. A navigation obstacle 3D shape set to bake with navigation mesh can be used to discard a geometry as well. Interesting. Navigation mesh script templates. The following script uses the navigation server to parse source geometry from the scene tree, bakes a navigation mesh, and updates a navigation region with the updated navigation mesh. The following script uses the navigation server to update a navigation region with procedurally generated navigation mesh data. Using navigation paths. Obtaining a navigation path. Navigation paths can be directly queried from the navigation server and do not require any additional nodes or objects as long as the navigation map has a navigation mesh to work with. To obtain a 2D path. Why am I yawning so much today? I do not know. Yeah. To obtain a 2D path, use navigation server 2D map get path map from to optimize navigation layers. What? To obtain a 3D path, use navigation server. Yeah. To obtain a 3D path, use navigation server 3D map get path map from to optimize navigation layers. It's the same. But you put 3D instead of 2D on the end of that first section. Because, of course you do. And they're basically the same function-wise. Just one's for 3D, one's for 2D, with a little bit of back-end shit. It smells hot out. I smell hot. Okay, I've had this weird thing. I don't know if it's common for anyone, but if I go outside on a hot summer day, I get this very distinct smell. It's like, I don't know, like wood chips? But it doesn't smell like wood. I don't know, it just smells hot. What does that smell? I genuinely do not know what that smell is, or where it comes from, but it happens on hot days. There's this very distinct smell. I don't know what it is, though. It's not a rocky smell. It's not a woody smell. Maybe it's grass? Could it be, like, grass? Maybe. Actually, yeah, that kind of makes sense. Grass. It might be grass. For more customization, for more customizable navigation path queries that require additional setup, see using navigation path query objects. One of the required parameters for the query is the RID of the navigation map. Each game world has a default navigation map automatically created. The default navigation map can be retrieved with getWorld2D map from any 2D node inheriting node, or getWorld3D .get navigation map from any node 3D inheriting node. The second and third parameters are the getting position and the starting position as vector 2 for 2D or vector 3 for 3D. If the optimized parameter is true, path positions will be shortened along polygon corners with an additional funnel algorithm pass. This works well for free movement on navigation meshes with unequally sized polygons, as the path will hug around corners along the polygon corridor found by the A-star algorithm. With small cells, the A-star algorithm creates a very narrow funnel corridor that can create ugly corner paths when used with grids. If the optimized parameter is false, path positions will be placed at the center of each polygon edge. This works well for pure grid movements on navigation meshes with equally sized polygons, as the path will go through the center of the grid cells. Outside of grids, due to polygons often covering large open areas with a single long edge, this can create paths with unnecessary long detours. Hi, Bella. Doggo. Oh, bye, Bella. They were here for 5 seconds and then they left. I wonder why. The return path by the navigation server will be packed vector 2 array for 2D or a packed vector 3 array for 3D. These are just a memory optimized array for vector positions. All position vectors inside the array are guaranteed to be inside a navigation polygon or navigation mesh. The path array, if not empty, has the navigation mesh position closest to the starting position at the first index, path 0 position. The closest available navigation mesh position to the target position is the last index, path size -1. Position all indexes between are the path points that an actor should follow to reach the target without leaving the navigation mesh. You can hear the dog. I don't know if that's my dog or the neighbor's dog, but it's somebody's dog that's barking. If the target position is on a different navigation mesh that is not merged or connected, the navigation path will lead to the closest possible position on the starting position navigation mesh. The following script moves a node 3D inheriting node along a navigation path using the default navigation map by setting the target position with set movement target. Okay. Using navigation path query objects. Did I read that already? I don't know. Tip: path query parameters expose various options to improve pathfinding performance or low memory consumption. They cater to more advanced pathfinding needs that the high-level nodes cannot always cover. See the respective option sections below. Navigation path query objects can be used together with navigation server query path to obtain a heavily customized navigation path, including optional metadata about the path. This requires more setup compared to obtaining a normal navigation path, but lets you tailor the pathfinding and provided path data to the different needs of a project. Navigation path query objects consist of a pair of objects, a navigation path query parameters, objects holding the customization options for the query, and a navigation path query result that receives regular updates with the resulting path and metadata from the query. 2D and 3D versions of navigation path query parameters are available as navigation path query parameters 2D and navigation path query parameters 3D respectively. 2D and 3D versions of navigation query result are available as navigation path query result 2D and navigation path query result 3D respectively, creating a basic path query. Both parameters and results are used as as a pair with the navigation server query path function. For the available customization options, see further below. See also the description for each parameter in the class reference. While not a strict requirement, both options are intended to be created once in advance, stored in a persistent variable for the agent, and reused for every follow-up path query with the updated parameters. Reusing the same objects improves performance when frequently created objects are allocated in memory. The following script creates the objects and provides a query path function to create new navigation paths. The resulting path is identical to using navigation server map.getPath while reusing the objects. Path post-processing options. Path edge-centered, path corridor funnel. Interesting. Interesting. Okay. Path query search travels from the closest navigation mesh polygon edge to the closest edge along the available polygons. If possible, it builds a polygon corridor towards the target position polygon. This raw search polygon corridor path is not very optimized and usually a bad fit for agents to travel along. Example, the closest edge point on a navigation mesh polygon might cause a huge detour for agents on larger polygons. In order to improve the quality of paths returned by the query, various path processing options exist. The path processing corridor funnel post-processing shortens path by funneling paths around corners inside the available polygon corridor. This is the default post-processing and usually also the most useful, as it gives the shortest path result inside the available polygon corridor. If the polygon corridor is already suboptimal, example due to a suboptimal navigation mesh layout, the funnel can snap to unexpected polygon corners, causing detours. The path post-processing corridor funnel post-processing shortens paths by funneling paths around corners inside the available polygon corridor. This is the default post-processing and usually also the most useful, as it gives shortest path result inside the available polygon corridor. If the polygon corridor is already suboptimal, wait, I already read that. Fuck. The path The path post-processing edge-centered post-processing forces all path points to be placed in the middle of the cross-polygon edges inside the available polygon corridor. The post-processing is usually only useful when used with strictly tile-like navigation mesh polygons. They're all evenly sized, and where the expected path following is also constrained to cell centers. Example, typical grid game with movement constrained to grid cell centers. The path post-processing, none. Post-processing returns a path as is how the path finding traveled inside the available polygon corridor. This post-processing is very useful for debug, as it shows how the path search traveled from closest edge point to closest edge point and what polygons is picked. A lot of unexpected or suboptimal path results can be immediately explained by looking at this raw path and polygon corridor. Path simplification can help steering agents or agents that jitter on this thin polygon edges. Path point difference with or without path simplification. If simplified path is enabled, a variant of the Raymer-Douglas Puker path simplification algorithm is applied to the path. This algorithm straightens paths by removing less relevant path points, depending on the simplify epsilon used. Path simplification helps with all kinds of agent movement problems in open fields that are caused by having many unnecessary polygon edges. Example, a terrain mesh when baking to a navigation mesh can cause an excessive polygon count due to all the small but for pathfinding almost meaningless height variations in the terrain. Path simplification also helps with steering agents because they only have more critical corner path points to aim for. Warning, path simplification is an additional final post-processing process of the path. It adds extra performance costs to the query, so only enable when actually needed. Note, path simplification is exposed on the navigation server as a generic function. It can be used outside of navigation queries for all kinds of position arrays as well. Path metadata. Tip, disabling unneeded path metadata options can improve performance and lower memory consumption. A path query can return additional metadata for every path point. The path metadata include types flag, collects all... Again, why am I yawning so much? Flag collects an array with the primitive information about the point owners. Example, if a point belongs to a region or link. The path metadata includes RIDS flag collection. The path metadata include RIDS flag collects an array with the RIDS of the point owners. Depending on point owner primitive, these RIDS can be used with these various navigation server functions related to regions or links. The path metadata include owners flag collects an array with the object IDs of the point owners. These object IDs can be used with the global scope instance from ID to retrieve the node behind that object instance. Example, a navigation region or navigation link node. By default, all path metadata is collected, as this metadata can be essential for more advanced navigation gameplay. Example, to know what path point maps to what object or node owner inside the scene tree. Example, to know if a path point is the start or end of a navigation link that requires scripted takeover. For the most basic path uses, metadata is not always needed. Path metadata collection can be selectively disabled to gain some performance and reduce memory consumption. Excluding or including regions. Tip, region filters can greatly help with performance on large navigation maps that are region partitioned. Query parameters allow limiting the pathfinding to specific region navigation meshes. If a large navigation map is well partitioned into smaller regions, this can greatly help with performance, as the query can skip a large number of polygons at one of the earliest checks in the path search. By default, and if left empty, all regions of the queried map are included. If a region map RID is added to the excluded regions array, the region's navigation mesh will be ignored in the path search. If a region RID is added to the included regions array, the region's navigation mesh will be considered in the path search, and also all other regions not included will be ignored as well. If a region ends up both including and excluding, it is considered excluded. Region filters are very effective for performance when paired with navigation region chunks that are aligned on a grid. This way, the filter can be set to only include the start position chunk and surrounding chunks instead of the entire navigation map. Even if the target might be outside the surrounding chunks, can always add more rings, the pathfinding will try to create a path to the polygon closest to the target. This usually creates a half paths heading in the general direction that are good enough, all for a fraction of the performance cost of a full map search. The following addition to the basic path query script showcases the idea how to integrate a region trunk mapping with the region filters. This is not a full working example. Path clipping and limits. Sensibly set limits can greatly help with performance on large navigation maps, especially when targets end up being unreachable. Clipping return paths to specific distances. Query parameters allow clipping return paths to specific lengths. These options clip the paths as a part of post-processing. The path is still searched as if at full length, so it will have the same quality. Path length clipping can help in creating paths that better fit constrained gameplay. Example, tactical games with limited movement ranges. The path return max length property can be used to clip the return path to a specific max length. The path return max radius property can be used to clip the return path inside a circle 2D or sphere 3D radius around the start position. Query parameters allow limiting the path search to only search up to a specific distance or specific number of search polygons. These options are for performance and affect the path search directly. The path search max distance property can be used to stop the path search when going over this distance from the start position. The path search max polygons property can be used to stop the path search when going over this search polygon number. When the path search is stopped by reaching a limit, the path resets and creates a path from the start position polygon to the polygon found so far that is closest to the target position. Warning: while good for performance, if path search limit values are set too low, they can affect the path quality very negatively. Depending on polygon layout and search pattern, the return paths might go into completely wrong directions instead of the direction of the target. Okay, I'm gonna go use the bathroom real quick. Yeah. I am here, just give me a second. Oh yeah, that should work well. Oh yeah. Yeah. So, I have a blanket on this chair because the seat is uncomfortable. And the way I had it before, it would get messed up a lot. So now that I have it hung over the back, hopefully it shouldn't get as messed up. Or maybe I should have had more on the length on the bottom. Alright, next section. Maybe I should split these sections up into their own videos. Maybe. Using navigation agents. Navigation agents are helper nodes that combine functionality for pathfinding, path following, and agent avoidance for node 2D or 3D inheriting parent node. They facilitate common calls to the navigation server API on behalf of the parent actor node in a more convenient manner for beginners. 2D and 3D version of navigation agents are available as Navigation Agent 2D and Navigation Agent 3D respectively. New navigation agent nodes will automatically join the default navigation map on the World 2D or World 3D. Navigation agent nodes are optional and not a hard equivalent to use the navigation system. Their entire functionality can be replaced with scripts and direct calls to the navigation server API. Tip: for more advanced uses, consider using navigation path query objects over navigation agent nodes. Navigation agent pathfinding. Navigation agents query a new navigation path on their current navigation map when their target position is set with a global position. The result of the pathfinding can be influenced with the following properties. The navigation layer's bitmask can be used to limit the navigation meshes that the agent can use. The pathfinding algorithm controls how the pathfinding travels through the navigation mesh polygons in the path search. The path processing sets if or how the raw path corridor can be found by the pathfinding is altered before it is returned. The path metadata flags enable the collection of additional path point metadata for returned by the path. The simplified path and simplify epsilon properties can be used to remove less critical points from the path. Warning: disabling path meta flags will disable related signal emissions on the agent. Navigation agent path following. After the target position has been set for the agent, the next position to follow in the path can be retrieved with the getNextPathPosition function. Once the next path position is received, move the parent actor node of the agent towards this path position with your own movement code. Note: the navigation system never moves the parent node of the navigation agent. The movement is entirely in the hands of users and their custom scripts. Navigation agents have their own internal logic to proceed with the current path and call for updates. The getNextPathPosition function is responsible for updating many of the agent's internal states and properties. The function should be repeatedly called once every physics process until its navigation finished, until that the path is finished. The function should not be called after the target position or path end has been reached, as it can make the agent jitter in place due to the repeated path updates. Always check very early in script with "is navigation finished" if the path is already finished. The following distance properties influence the path following behavior. At path desired distance from the next path position, the agent advances its internal path index to the subsequent next path position. At target desired distance from the target path position, the agent considers the target position to be reached in the path at its end. At path max distance from the ideal path to the next path position, the agent requests a new path because it was pushed too far off. The important updates are all triggered with the getNextPathPosition function when called in physics process. Navigation agents can be used with process but are still limited to a single update that happens in physics process. Script examples for various nodes commonly used with the navigation agents can be found further below. Path following common problems. There are some common user problems and important caveats to consider when writing agent movement scripts. The path is returned empty. If an agent queries a path before the navigation map synchronization example in a ready function, the path might return empty. In this case, the getNextPathPosition function will return the same position as the agent parent node, and the agent will consider the path end reached. This is fixed by making a deferred call or using a callback Example: waiting for a navigation map changed signal. The agent is stuck dancing between two positions. This is usually caused by very frequent path updates every single frame, either deliberate or by accident. Example: max path distance set too short. The pathfinding needs to find the closest position that are valid on navigation mesh. If a new path is requested every single frame, the first path positions might end up switching constantly in front and behind the agent's current position, causing it to dance between the two positions. The agent is backtracking sometimes. If an agent moves very fast, it might overshoot the path desired distance check without ever advancing the path index. This can lead to the agent backtracking to the path point now behind it until it passes the distance check to increase a path index. Increase the desired distances accordingly to your agent speed, and update rate usually fixes this, as well as a more balanced navigation mesh polygon layout with not too many polygon edges cramped together in small spaces. The agent is sometimes looking backwards for a frame. Same as with stuck dancing agents between two positions, this is usually caused by very frequent path updates every single frame. Depending on your navigation mesh layout, and especially when an agent is directly placed over a navigation mesh edge or edge connection, expect path position to be sometimes slightly behind your actor's current orientation. This happens due to precision issues and cannot always be avoided. This is usually only a visible problem if actors are instantly rotated to face the current path position. Navigation agent avoidance. This section explains how to use the navigation avoidance specific to navigation agents. In order for navigation agents to use the avoidance feature, the avoidance enabled property must be set to true. The velocity computed signal of the navigation agent node must be connected to receive the safe velocity calculation result. Set the velocity of the navigation agent node in physics process to update the agent with the current velocity of the agent's parent node. While avoidance is enabled on the agent, the safe velocity vector will be received with the velocity computed signal every physics frame. This velocity vector should be used to move the navigation agent's parent node in order to avoidance collision with other avoidance using agents or avoidance obstacles. Note, only the other agents on the same map that are registered for avoidance themselves will be considered the avoidance calculation. Note, the navigation agent must be supplied with a target position attribute, even if you are only using the agent for avoidance. Otherwise, the safe velocity received from the velocity computed signal will always be the zero vector. The following navigation agent properties are relevant for avoidance. The property height is available in 3D only. The height together with the current global y-axis position of the agent determines the vertical placement of the agent in the avoidance simulation. Agents using the 2D avoidance will automatically ignore their agents or obstacles that are below or above them. The property radius controls the size of the avoidance circle, or in case of 3D sphere, around the agent. This area describes the agent's body and not the avoidance maneuver distance. The property neighbor distance controls the search radius of the agent when searching for other agents that should be avoided. A lower value reduces processing cost. The property max neighbors controls how many other agents are considered in the avoidance calculation if they all have overlapping radius. A lower value reduces processing cost, but a too low value may result in agents ignoring the avoidance. The properties time horizon agents and time horizon obstacles control the avoidance prediction time for other agents or obstacles in seconds. When agents calculate their safe velocities, they choose velocities that can be kept for this amount of seconds without colliding with another avoidance object. The prediction time should be kept as low as possible, as agents will slow down their velocities to avoid collision in that time frame. The property max speed controls the maximum velocity allowed for agent's avoidance calculation. If the agent's parent moves faster than this value, the avoidance safe velocity might not be accurate enough to avoid collision. The property use 3D avoidance switches the agent between 2D avoidance XZ axis and the 3D avoidance XYZ axis on the next update. Note that 2D avoidance and 3D avoidance run in separate avoidance simulations, so agents split between them do not affect each other. The properties avoidance layers and avoidance masks are bit masks similar to example physics layers. Agents will only avoid other avoidance objects that are not on an avoidance layer that matches at least one of their own avoidance mask bits. The avoidance priority makes agents with a higher priority ignore agents with a lower priority. This can be used to give certain agents more importance in the avoidance simulation. Example, important non-playable characters without constantly changing their entire avoidance layers or mask. Avoidance exists in its own space and has no information from navigation meshes or physics collisions. Behind the scene avoidance agents are just circles with different radius on a flat 2D plane or spheres in an otherwise empty 3D space. Navigation obstacles can be used to add some environment constraints to the avoidance simulation. See using navigation objects. Note: avoidance does not affect the pathfinding. It should be seen as an additional option for constantly moving objects that cannot be rebaked to a navigation mesh efficiently in order to move around them. Note: RVO avoidance makes implicit assumptions about natural agent behavior. Example, that agents move on unreasonable passing sides that can be assigned when they encounter each other. This means that very clinical avoidance test scenarios will commonly fail. Example, agents move directly against each other with perfect opposite velocities will fail because the agents cannot get their passing sides assigned. Using the Navigate Agent Avoidance Enabled property is the preferred option to toggle avoidance. The following code snippets can be used to toggle avoidance on agents, create or delete avoidance callbacks, or switch avoidance modes. Navigation Agent Script Templates. The following sections provide script templates for nodes commonly used with navigation agents. Using navigation obstacles. 2D and 3D versions of navigation obstacle nodes are available as navigation obstacle 2D and navigation obstacle 3D respectively. Navigation obstacles are dual purpose in that they can affect both the navigation mesh baking and the agent avoidance. With affect navigation mesh enabled, the obstacle will affect navigation mesh when baked. With avoidance enabled, the obstacle will affect avoidance agents. Tip: avoidance is enabled by default. If the obstacle is not used for avoidance, disable enabled avoidance to save performance. Objects in navigation mesh. Navigation obstacles affecting navigation mesh baking. For navigation mesh baking, obstacles can be used to discard parts of all other source geometry inside the obstacle shape. This can be used to stop navigation meshes being baked in unwanted places. Example, inside solid geometry like thick walls or on top of other geometry that should not be included for gameplay like roofs. Navigation obstacles discard of unwanted navigation mesh. An obstacle does not add geometry in the baking process, it only removes geometry. It does so by nullifying all the voxel cells with rasterized source geometry that are within the obstacle shape. As such, its effect and shape detail is limited to the cell resolution used by the baking process. For more details on the navigation mesh baking, see Use Navigation Meshes. The property affect a navigation mesh makes the obstacle contribute to the navigation mesh baking. It will be parsed or unparsed like all other node objects in a navigation mesh baking process. The carve navigation mesh property makes shape unaffected by offsets of the baking. Example, the offset added by the navigation mesh agent radius. It will basically act as a stencil and cut into the already offset navigation mesh surface. It will still be affected by further post-processing of the baking process, like edge simplification. The obstacle shape and placement is defined with the height and vertices properties and the global position of the obstacle. The y-axis value of any vector 3 used for the vertices is ignored as the obstacle is placed on a flat horizontal plane. When baking navigation meshes and scripts, obstacles can be added procedurally as a projected obstruction. Obstacles are not involved in the source geometry parsing, so adding them just before baking is enough. Obstacles and agent avoidance. For avoidance navigation, obstacles can be used either as static or dynamic obstacles to affect avoidance-controlled agents. When used statically, navigation objects constrain avoidance-controlled agents outside or inside a polygon-defined area. When used dynamically, navigation obstacles push away avoidance-controlled agents in a radius around them, static avoidance obstacles. An avoidance obstacle is considered static when its vertices property is populated with an outline array of positions to form a polygon. Static obstacles act as hard do-not-cross boundaries for avoidance using agents. Example similar to physics collision, but for avoidance. Static obstacles define their boundaries with an array of outline vertices, positions, and in case of 3D, with an additional height property. Static obstacles only work for agents that use 2D avoidance mode. Static obstacles define through winding order of the vertices if agents are pushed out or sucked in. Static obstacles cannot change their position. They can only be warped to a new position and rebuilt from scratch. Static obstacles, as a result, are ill-suited for usages where the position is changed every frame, as the constant rebuild has a high performance cost. Static obstacles that are warped to another position cannot be predicted by agents. This creates the risk of getting agents stuck should a static obstacle be warped on top of agents. When the 2D avoidance is used in 3D, the y-axis of vector 3 vertices is ignored. Instead, the global y-axis position of the obstacle is used as the elevation level. Agents will ignore static obstacles in 3D that are below or above them. This is automatically determined by global y-axis position of both obstacle and agent as the elevation level as well as their respective height properties. Dynamic avoidance obstacles. An avoidance obstacle is considered dynamic when its radius property is greater than 0. Dynamic obstacles act as a soft "please move away from me" object for avoidance using agents. Examples similar to how they avoid other agents. Dynamic obstacles define their boundaries with a single radius for a 2D circle, or in case of 3D avoidance, a sphere shape. Dynamic obstacles can change a position every frame without additional performance cost. Dynamic obstacles with a set velocity can be predicted in their movement by agents. Dynamic obstacles are not a reliable way to constrain agents in crowded or narrow spaces. While both static and dynamic properties can be active at the same time on the same obstacle, this is not recommended for performance. Ideally, when an obstacle is moved, the static vertices are removed and instead the radius activated. When the obstacle reaches the new final position, it should gradually enlarge its radius to push all other agents away. With enough created safe space around the obstacle, it should add the static vertices again and remove the radius. This helps avoid getting agents stuck in the suddenly appearing static obstacle when the rebuilt static boundary is finished. Similar to agents, the obstacles can make use of the avoidance layer's bit mask. All agents with a matching bit on their own avoidance mask will avoid the obstacle. Procedural obstacles. New obstacles can be created in a script without a node by using the navigation server directly. Obstacles created with scripts require at least a map and a position for dynamic use. A radius is required. For static use, an array of vertices is required. It sounds like my mother and sister are home. Bella! Hi, Bella. Bye, Bella. Use navigation links. Navigation links are used to connect navigation mesh polygons from Navigation Region 2D and Navigation Region 3D over arbitrary distances or pathfinding. For pathfinding, navigation links are also used to consider movement shortcuts and pathfinding available through interacting with gameplay objects, example ladders, jump pads, or teleports. 2D and 3D versions of navigation jump links nodes are available as Navigation Link 2D and Navigation Link 3D respectively. Different navigation regions can connect their navigation meshes without the need for a navigation link, as long as they have overlapping edges or edges that are within navigation map. Edge connection margin. As soon as the distance becomes too large, building valid connections becomes a problem that navigation links can solve. See using navigation regions to learn more about the use of navigation regions. See connecting navigation meshes to learn more about how to connect navigation meshes. Navigation links share many properties with navigation regions like navigation layers. Navigation links add a single connection between two positions over an arbitrary distance compared to navigation regions that add a more local traversable area with a navigation mesh resource. Navigation links have a start position and end position, and can go in both directions when bidirectional is enabled. When placed, a navigation link connects the navigation mesh polygons closest to its start position and end position within search radius for pathfinding. The polygon search radius can be configured globally in the project settings under Navigation 2D or 3D default link connection radius. For set for navigation map individually, use the navigation server map set link connection radius function. Both start position and end position have debug markers in the editor. The arrows indicate which direction the link can be traveled across, and the visible radius of the position shows the polygon search radius. All navigation mesh polygons inside are compared, and the closest is picked for the edge connection. If no valid polygon is found, then the search radius in the navigation link gets disabled. I think that's just flavor text. No, it's not. The link debug visuals can be changed in the editor project settings under Debug Shapes Navigation. The visibility of the debug can also be controlled in the editor 3D viewport gizmo menu. A navigation link does not provide any specialized movement through the link. Instead, when an agent reaches the position of a link, game code needs to react, example, through area triggers, and provides means for the agent to move through the link to end up at the link's other position, example, through teleport or animation. Without that, an agent will attempt to move itself along the path of the link. You could end up with an agent walking over a bottomless pit instead of waiting for a moving platform, or walking through a teleport and proceeding through a wall. Navigation link script templates. The following script uses the navigation server to create a navigation link. Using navigation layers. Navigation layers are an optional feature to further control which navigation meshes are considered in a path query. They work similar to how physics layers control collision between collision objects, or how visual layers control what is rendered to the viewport. Navigation layers can be named in the project settings, the same as physics layers for visual layers. If a region has not a single compatible navigation layer with the navigation layers parameter of a path query, this region's navigation mesh will be skipped in pathfinding. See using navigation paths for more information on querying the navigation server for paths. Navigation layers are a single int value that is used as a bitmask. Many navigation related nodes have set navigation layer value and get navigation layer value functions to set and get layer number directly without the need for more complex bitwise operations. In scripts, the following helper functions can be used to work with the navigation layers bitmask. Changing navigation layers for path queries is a performance-friendly alternative to enabling or disabling entire navigation regions. Compared to region changes, a navigation path query with different navigation layers does not trigger large-scale updates on the navigation server. Changing the navigation layers of navigation agent nodes will have an immediate effect on the next path query. Changing the navigation layers of regions will have an effect after the next navigation server sync. Navigation debug tools. The debug tools properties and functions are only available in Godot debug builds. Do not use any of them in code that will be part of a release build. But what if I wanna have an available setting for players to turn on debug mode so that they can see how the game works? I actually really wanna like allow people to see my work, because I think that the code of various games is so interesting to look at. I haven't looked at any myself, but like, just looking at how the game functions is so cool in my opinion. Like, like for example, with Minecraft, they deobfuscated their code at some point this year, I think. Or is it last year? Sometime somewhat recently. And, like, it is so interesting. It allows for great modding, it allows for more available modding capability. And of course, finding exploits or for players to find bugs within the game that can be reported to Mojang. Enabling navigation debug. The navigation debug visualizations are enabled by default inside the editor. To visualize navigation meshes and connections at runtime 2, enable the options visible navigation in the editor debug menu. In Godot debug builds, the navigation debug can also be toggled through the navigation server singletons from scripts. Debug visualizations are currently based on nodes in the scene tree. If the Navigation Server 2D or Navigation Server 3D APIs are used exclusively, then changes will not be reflected by the debug navigation tools. Navigation debug settings. The appearance of navigation debug can be changed in the project settings under Debug Shapes Navigation. Certain debug features can also be enabled or disabled at any time, but many require a scene restart or to take effect. Debug navigation mesh polygons. If Enable Edge Lines is enabled, the edges of navigation mesh polygons will be highlighted. If Enable Edge Lines X-ray is also enabled, the edges of navigation meshes will be visible through geometry. If Enable Geometry Face Random Color is enabled, the color of each navigation mesh face will be mixed with a random color that is itself mixed with the color specified in Geometry Face Color. Debug Edge Connections. When two navigation meshes are connected with an edge connection margin distance, the connection is overlaid. The color of the overlay is controlled by edge connection color. The connections can be made visible through geometry with Enable Edge Connections X-ray. Note, edge connections are only visible when the navigation server is active. Debug performance. To measure navigation server performance, a dedicated monitor can be found within the editor debugger under Debugger Monitors Navigation Process. Navigation process shows how long the navigation server spends updating its internals this update frame in milliseconds. Navigation process works similar to process for visual frame rendering and physics. Physics process for collision and fixed updates. Navigation process accounts for all updates to navigation maps, navigation regions, and navigation agents, as well as all avoidance calculations for the update frame. Note, navigation process does not include pathfinding performance because pathfinding operates on the navigation map data independently from the server process data. Navigation process should be in general kept as low and as stable as possible for runtime performance to avoid frame rate issues. Note that since the navigation server process update happens in the middle of the physics update, an increase in navigation process will automatically increase physics process by the same amount. Navigation also provides more detailed statistics about the current navigation-related objects and navigation map composition on the navigation server. Navigation statistics shown here cannot be judged as good or bad for performance, as it depends entirely on the project what can be considered as reasonable or horribly excessive. Navigation statistics help with identifying performance bottlenecks that are less obvious because the source might not always have a visible representation. Example, pathfinding performance issues created by overly detailed navigation meshes with thousands of edges, polygons, or problems caused by procedural navigation gone wrong. Connection navigation meshes. Different navigation meshes are automatically merged by the navigation server when at least two vertex positions of one edge exactly overlap. To connect over arbitrary distances, see using navigation links. The same is true for multiple navigation polygon resources. As long as their outline points overlap exactly, the navigation server will merge them. Navigation polygon outlines must be from different navigation polygon resources to connect. Overlapping or intersecting outlines on the same navigation polygon will fail the navigation mesh creation. Overlapping or intersecting outlines from different navigation polygons will often fail to create the navigation region edge connections on the navigation server and should be avoided. Warning, Exactly means exactly for the vertex position merge. Small float errors that happen quite regularly with imported meshes will prevent a successful vertex merge. Alternatively, navigation meshes are not merged but still considered as connected by the navigation server when their edges are nearly parallel within distance to each other. The connection distance is defined by the edge connection margin for each navigation map. In many cases, navigation mesh edges cannot properly connect when they partly overlap. Better avoid any navigation mesh overlap at all time for a consistent merge behavior. If navigation debug is enabled as the navigation server is active, the established navigation mesh connections will be visualized. See Navigation Debug Tools for more info about navigation debug options. The default 2D connection margin can be changed in the project settings under Navigation 2D Default Edge Connection Margin. The default 3D, same, but instead of 2D, it's 3D. The edge connection margin value of any navigation map can also be changed at runtime with the Navigation Server API. Note, changing the edge connection margin will trigger full update of all navigation mesh connections on the navigation server. Support different actor types. To support different actor types due to, example, their sizes, each type requires its own navigation map and navigation mesh baked with an appropriate agent, radius, and height. The same approach can be used to distinguish between, example, land, walking, swimming, or flying agents. Note, agents are exclusively defined by a radius and height value for baking navigation meshes. Pathfinding and avoidance. More complex shapes are not supported. Oh, Jesus. Support different actor locomotion. To support different actor locomotion like crouching or crawling, a similar map setup as supporting support different actor types is required. Bake different navigation meshes with an appropriate height for crouched or crawling actors so they can find paths through those narrow sections in your game world. When an actor changes locomotion state, example, stands up, starts crouching or crawling, query the operation map for a path. If the avoidance behavior should also change with the locomotion, example, only avoid while standing or only avoid other agents in the same location state, switch the actor's avoidance agent to another avoidance map with each locomotion change. Note, while a path query can be executed immediately for multiple maps, the avoidance agent map switch will only take effect after the next server synchronization. Support different actor area access. A typical example for different area access in gameplay are doors that connect rooms with different navigation meshes and are not accessible by all actors all the time. Add a navigation region at the door position, add an appropriate navigation mesh, the size of the door that can connect with the surrounding navigation meshes. In order to control access, enable or disable navigation layer bits, so path queries that use the same navigation layer bits can find a path through the door navigation mesh. The bit mask can act as a set of door keys or abilities, and only actors with at least one matching and enabled bit layer in their pathfinding query will find a path through this region. See using navigation layers for more information on how to work with navigation layers and the bit mask. The entire door region can also be enabled, disabled if required, but if disabled will block access for all path queries. Prefer working with navigation layers and path queries whenever possible, as enabling or disabling navigation layers on a region triggers a costly recalculation of the navigation map connections. Warning, changing navigation layers will only affect new path queries, but not automatically update existing paths. Optimizing navigation performance. Common navigation-related performance problems can be categorized into the following topics. Performance problems with parsing scene tree nodes for navigation mesh baking. Performance problems with baking the actual navigation mesh. Performance problems with navigation agent path queries. Performance problems with the actual path search. Performance problems with synchronizing the navigation map. In the following sections, information can be found on how to identify and fix or at least mitigate their impact on frame rates. Performance problems with parsing scene tree nodes. Tip: prefer using simple shapes with as few edges as possible. Example, nothing rounded like a circle, sphere, or torus. Prefer using physics collision shapes over complex visual meshes as source geometry, as meshes need to be copied from the GPU and are commonly much more detailed than necessary. In general, avoid using a very complex geometry as source geometry for baking navigation meshes. Example, never use a very detailed visual mesh, as parsing its shape to data arrays and voxelizing it for the navigation mesh baking will take a long time for no real quality gain on the final navigation mesh. Instead, use a very simplified level of detail version of a shape. Even better, use a very primitive shapes like boxes and rectangles that only roughly cover the same geometry, but still yield a baked result good enough for pathfinding. Prefer using simple physics collision shapes over visual meshes. As a source geometry for baking navigation meshes, physics shapes are by default very limited and optimized shapes that are easy and quick to parse. A visual mesh, on the other hand, can range from simple to complex. On top, to gain access to visual mesh data, the parser needs to request the mesh data arrays from the rendering server, as visual mesh data is stored directly on the GPU and is not cached on the CPU. This requires locking the rendering server thread and can severely impact frame rate at runtime while the rendering runs multi-threaded. If the rendering runs single-threaded, the frame rate impact might be even worse and the mesh parsing might freeze the entire game for a few seconds on complex meshes. Performance problems with navigation mesh baking. Tip: at runtime, always prefer to use a background thread for baking navigation meshes. Increase navigation mesh cell size and cell height to create less voxels. To change the sample partition type from watershed to monotone or layers to gain baking performance. Warning: never scale source geometry with nodes to avoid precision errors. Most scale applies only visually, and shapes that are very large at their base scale requires a lot of extra processing even while downscaled. Baking navigation meshes at runtime should always be done in a background thread if possible. Even small-sized navigation meshes can take far longer to bake than what is possible to squeeze into a single frame, at least if that frame should stay at a bearable level. Complexity of source geometry data parsed from scene tree nodes has big impact on baking performance, as everything needs to be mapped to a grid or voxels for runtime. For runtime baking performance, the navigation mesh cell size and cell height should be set as high as possible without causing navigation mesh quality problems for a game. If cell size or cell height is set too low, the baking is forced to create an excessive amount of voxels to process the source geometry. If the source geometry spans over a very large game world, it is even possible that the baking process runs out of memory in the middle and crashes the game. The partition type can also be lowered depending on how complex a game source geometry is to gain some performance. Example, games with mostly flat surfaces with blocky geometry can get away with the monotone or layers mode that are a lot faster to bake. Example, because they require no distance field pass. Never scale source geometry with nodes. Not only can it result in a lot of precision errors with wrongly matched vertices and edges, but also some scaling only exists as visuals and not in actual parsed data. Example, if a mesh is downscaled visually in the editor. Example, the scale set to 0.001 on a mesh instance, the mesh still requires a gigantic and very complex voxel grid to be processed for the baking. Performance problems with navigation agent path queries. Tip: avoid unnecessary path resets and queries every frame in navigation agent scripts. Avoid updating all navigation agent paths in the same frame. Logical errors and wasteful operations in the custom navigation agent scripts are very common causes of performance issues. Example, watch out for resetting the path every single frame. By default, navigation agents are optimized to only query new paths when the target position changes, the navigation map changes, or they are forced too far away from the desired path instance. Example, when AI should move to the player. The target position should not be set to the player position every single frame, as this queries a new path every frame. Instead, the distance from the current target position to the player position should be compared, and only when the player has moved too far away a new target position should be set. Do not check beforehand if a target position is reachable every frame. What looks like an innocent check is the equivalent of an expensive path query behind the scene. If the plan is to request a new path anyway, should the position be reachable. A path should be queried directly by looking at the last position of the return path, and if that position is in a reachable distance to the checked position, it answers the is the position reachable question. This avoids doing the equivalent of 2 full path queries every frame for the same navigation agent. Divide the total number of navigation agents into update groups or use random timers so that they do not all request new paths in the same frame. Performance problems with the actual path search. Tip: optimize over detailed navigation meshes by reducing the amount of polygons and edges. The cost of the actual path search correlates directly with the amount of navigation mesh polygons and edges and not the real size of the game world. If a giant game world uses very optimized navigation meshes with only a few polygons that covers large areas, performance should be acceptable. If the game world is splintered into very small navigation meshes that each have tiny polygons, like for tile maps, pathfinding performance will be reduced. A common problem is a sudden performance drop when a target position is not reachable in a path query. This performance drop is normal and the result of a too large, too optimized navigation mesh with way too much polygons, the edges to search through in a normal path search, where the target position can be reached quickly and pathfinding will do an early exit as soon as the position is reached, which can hide this lack of optimization for a while. If the target position cannot be reached, the pathfinding has to do a far longer search through the available polygons to confirm that the position is absolutely not reachable. Performance problems with navigation map synchronization. Tip: merge navigation meshes polygons by vertex instead of by edge connections wherever possible. When changes are made to example navigation meshes or navigation regions, the navigation server needs to synchronize a navigation map. Depending on the complexity of the navigation meshes, this can take a significant amount of time, which may impact the frame rate. The navigation server merges navigation meshes either by vertex or by edge connection. The merge by vertex happens when the two vertex of two different edges land in the same map grid cells. This is a rather quick and low-cost operation. The merge by edge connection happens in a second pass for all still unmerged edges. All the free edges are checked for possible edge connections by both distance and angle, which is rather costly. So apart from the general rule to have as few polygon edges as possible, as many edges as possible should be merged by vertex up front, so only a few edges are left for the more costly edge connection calculation. The debug navigation performance monitor can be used to get statistics on how many polygons and edges are available and how many of them are unmerged or not merged by vertex. If the ratio between vertex merged and edge connections is way off, vertex should be significantly higher. The navigation meshes are properly created or placed very inefficient. Networking. Well, I'm not going to be using multiplayer in my game, so I don't need to worry about this. Performance! Yay. Introduction. Godot follows a balanced performance philosophy. In the performance world, there are always trade-offs, which consist of trading speed for usability and flexibility. Some practical examples of this are: rendering large amounts of objects efficiently is easy, but when a large scene must be rendered, it can become difficult. To solve this, visibility computation must be added to the rendering. This makes rendering less efficient, but at the same time, fewer objects are rendered. Therefore, the overall rendering efficiency is improved. Configuring the properties of every material for every object that needs to be rendered is also slow. To solve this, the objects are sorted by material to reduce the costs. At the same time, sorting has a cost. In 3D physics, a similar situation happens. The best algorithms to handle large amounts of physics objects, such as SAP, are slow at insertion or removal of objects and raycasting. Algorithms that allow faster insertion and removal, as well as raycasting, will not be able to handle as many active objects. And there are many more examples of this. Game engines strive to be general purpose in nature. Balanced algorithms are always favored by algorithms that might be fast in some situations and slow in others, or algorithms that are fast but more difficult to use. Godot is not an exception to this. While it is designed to have backends swappable for different algorithms, the default backends prioritize balance and flexibility over performance. With this clear, the aim of this tutorial section is to explain how to get the maximum performance out of Godot. While the tutorials can be read in any order, it is a good idea to start from general optimization tips. Common general optimization tips. Okay. General optimization tips. Introduction. In an ideal world, computers would run at infinite speed. The only limit to what we could achieve would be our imagination. However, in the real world, it's all too easy to produce software that will bring even the fastest computer to its knees. Thus, designing games and other software is a compromise between what we would like to be possible and what we can realistically achieve while maintaining good performance. To achieve the best results, we have two approaches: work faster, work smarter, and preferably, we will use a blend of the two. Smoke and mirrors. Part of working smarter is recognizing that in games we can often get the player to believe that they're in a world that's far more complex, interactive, and graphically exciting than it really is. A good programmer is a magician and should strive to learn the tricks of the trade while trying to invent new ones. The nature of slowness. To the outside observer, performance problems are often lumped together, but in reality there are several different kinds of performance problems. A slow process that occurs every frame, leading to a continuously low frame rate, an intermittent a process that causes spikes of slowness leading to stalls, a slow process that occurs outside of normal gameplay, for instance when loading a level. Each of these are annoying to the user but in different ways. Measuring performance. Probably the most important tool for optimization is the ability to measure performance, to identify where bottlenecks are, and to measure the success of our attempts to speed them up. There are several methods of measuring performance, including putting a start or stop timer around the code of interest, using the Godot profiler, using external CPU profilers, using external GPU profilers debuggers such as NVIDIA Insight Graphics, Radeon GPU Profiler PIX, Direct3D 12 only, Xcode, Metal only, or ARM Performance Studio. Checking the frame rate with VSync disabled. Third-party utilities such as Riva Tuner Statistics Server, Windows, Special K, Windows, or Mango HUD, Linux can also be useful here, using an unofficial debug menu add-on. Be very aware that the relative performance of different areas can vary on different hardware. It's often a good idea to measure timing on more than one device. This is especially the case if you're targeting mobile devices. Limitations. CPU profilers are often the go-to method for measuring performance. However, they don't always tell the whole story. Bottlenecks are often on the GPU as a result of instructions given by the CPU. Spikes can occur in the operating system processes outside of Godot as a result of instructions used in Godot, for example, dynamic memory allocation. You may not always be able to profile specific devices like a mobile phone due to the initial setup required. You may have to solve performance problems that occur on hardware you don't have access to. As a result of these limitations, you often need to use detective work to find out where bottlenecks are. Detective work. Detective work is a crucial skill for developers in both in terms of performance and also in terms of bug fixing. This can include hypothesis testing and binary search. Hypothesis testing. Say, for example, that you believe sprites are slowing down your game. You can test this hypothesis by measuring the performance when you add more sprites or take some away. This may lead to a further hypothesis. Does the size of the sprite determine the performance drop? You can test this by keeping everything the same but changing the sprite size and measuring performance. Binary search. If you know that frames are taking much longer than they should but you're not sure where the bottleneck lies, you could begin by commenting out approximately half the routines that occur on a normal frame. Has the performance improved more or less than expected? Once you know which of the two halves contains a bottleneck, you can repeat this process until you've pinned down the problematic area. Profilers. Profilers allow you to time your program while running it. Profilers then provide results telling you what percentage of time was spent in different functions and areas, and how often functions were called. This can be very useful to both identify bottlenecks and to measure the results of your improvements. Sometimes attempts to improve performance can backfire and lead to slower performance. Always use profiling and timing to guide your efforts. For more info about using Godot's built-in profiler, see the profiler. Principles. Donald Knuth said, programmers waste enormous amounts of time thinking about or worrying about the speed of non-critical parts of their games, or of their programs. And these attempts at efficiency actually have a strong negative impact when debugging it, and maintenance are considered. We should forget about small efficiencies. Say about 97% of the time, premature optimization is the root of all evil. Yet we should not pass up our opportunities in that critical 3%. The messages are very important. Developer time is limited. Instead of blindly trying to speed up all aspects of a program, we should concentrate our efforts on the aspects that really matter. Efforts at optimization often end up with code that is harder to read and debug than non-optimized code. It is in our interest to limit this to areas that will really benefit. Just because we can optimize a particular bit of code, it doesn't necessarily mean that we should. Knowing when and when not to optimize is a great skill to develop. One misleading aspect of the quote is that people tend to focus on the subquote, premature optimization is the root of all evil. While premature optimization, by definition, undesirable performant software is the result of performant design. Performant design. The danger with encouraging people to ignore optimization until necessary is that it conveniently ignores that the most important time to consider performance is at the design stage, before a key has even hit a keyboard. If the design or algorithms of a program are inefficient, then no amount of polishing the details later will make it run fast. It may run faster, but it will never run as fast as as a program designed for performance. This tends to be far more important in game or graphics programming than in general programming. A performant design, even without low optimization, will often run many times faster than a mediocre design with low-level optimization. Incremental design. Of course, in practice, you'll have prior knowledge. You are unlikely to come up with the best design the first time. Instead, you'll often make a series of versions of a particular area of code, each taking a different approach to the program, until you come to a satisfactory conclusion. It's important to not spend too much time on the details on this stage until you have finalized the overall design. Otherwise, much of your work will be thrown out. It's difficult to give general guidelines for performant design because it's so dependent on the problem. One point worth mentioning, though, on the CPU side is that modern CPUs are nearly always limited by memory bandwidth. This has led to a resurgence in data-oriented design, which involves designing data structures and algorithms for cache locality of data and linear access rather than jumping around in memory. The optimization process. Assuming we have a reasonable design and taking our lessons from Knuth, our first step is optimization. In optimization should be to identify the biggest bottlenecks, to the slowest functions, the low-hanging fruit. Once we've successfully improved the speed of the slowest area, it may no longer be the bottleneck. So we should test or profile again and find the next bottleneck on which to focus. The process is thus: profile or identify bottleneck, optimize bottleneck, return to step 1. Optimizing bottlenecks. Some profilers will even tell you which part of a function, which data access calculations, are slowing things down. As we design, you should concentrate your efforts first on making sure the algorithm and data structures are the best they can be. Data access should be local to make best of CPU cache, and it can often be better to use compact storage of data, again, always profiled to test results. Often you pre-calculate heavy computations ahead of time. This can be done by performing the computation when loading a level, by loading a file containing pre-calculated data, or by storing the results of complex calculations into a script constant and reading its value. Once algorithms and data are good, you can often make small changes in routines which improve performance. For instance, you can move some calculations outside of loops, or transform nested for loops into non-nested loops. This should be feasible if you know a 2D array's width or height in advance. Always retest your timing bottlenecks after making each change. Some changes will increase speed, others may have negative effect. Sometimes a small positive effect will be outweighed by the negatives of more complex code, and you may choose to leave out that optimization. Appendix: bottleneck math. The proverb, "a chain is only as strong as its weakest link," applies directly to performance optimization. If your project is spending 90% of the time in function A, then optimizing A can have a massive effect on performance. In this example, improving this bottleneck A by a factor of 9 decreases overall frame time by 5 times, while increasing frames per second by 5 times. However, if something else is running slowly and also bottlenecking your project, then the same improvement can lead to less dramatic gains. In this example, even though we have hugely optimized function A, the actual gain in terms of frame rate is quite small. In games, things become even more complicated because the CPU and GPU run independently of one another. Your total frame time is determined by the slower of the two. In this example, we optimize the CPU hugely again, but the frame time didn't improve because we are GPU bottlenecked. Optimization using servers. Engines like Godot provide increased ease of use thanks to their high-level constructs and features. Most of them are accessed and used via the scene system. Using nodes and resources simplifies project organization and asset management in complex games. There are several drawbacks to this. There is an extra layer of complexity. Performance is lower than when using simple APIs directly. It is not possible to use multiple threads to control them. More memory is needed. In some cases, it is not really a problem. Godot is well optimized, and most operations are handled with signals, which means no polling is required. Still, sometimes we want to extract better performance from the hardware when other avenues of optimization have been exhausted. For example, dealing with tens of thousands of instances for something that needs to be processed every frame can be a bottleneck. This type of situation makes programmers regret they are using a game engine and wish they could go back to a more handcrafted low-level implementation of game code. Still, Godot is designed to work around this problem. See also, you can see how using low-level servers works in action using the Bullet Shower demo project. Servers. One of the most interesting design decisions for Godot is the fact that the whole scene system is optional. While it is not possible to compile it out, it can be completely bypassed. At the core, Godot uses the concept of servers. They are low-level APIs to control rendering, physics, sound, etc. The scene system is built on top of them and uses them directly. The most common servers are rendering server, handles everything related to graphics; physics server 3D handles everything related to 3D physics; physics server 2D handles everything related to 2D physics; audio server handles everything related to audio. Explore their APIs, and you'll realize that all the functions provided are low-level implementations of everything Godot allows you to do using nodes. RIDs. The key to using servers is understanding the resource ID. RID. Objects. These are opaque handles to the server implementation. They are allocated and freed manually. Almost every function in these servers requires RIDs to access the actual resource. Most Godot nodes and resources contain these RIDs from the servers and internally, and they can be obtained with different functions. In fact, anything that inherits resource can be directly casted to an RID. Not all resources contain an RID, though. In such cases, the RID will be empty. The resource can then be passed to server APIs as an RID. Warning: resources are reference counted. See ref counted, and references to resources RID are not counted when determining whether the resource is still in use. Make sure to keep performance to the resource outside the server, otherwise both the resource and its RID will be erased. For nodes, that are many functions available. For canvas item, the canvas item get canvas item method will return the canvas item RID in the server. For canvas layer, the canvas layer get canvas method will return the canvas RID in the server. For viewport, the viewport get viewport rid method will return the viewport RID in the server. For 2D, the world 2D resource obtainable in the viewport and canvas item nodes contains functions to get the rendering server canvas and physics server 2D space. This allows creating 2D objects directly with the server API and using them. For 3D, the world 3D resource obtainable in viewport and 3D nodes contains functions to get rendering server scenario and its physics server space. This allows creating 3D objects directly with the server API and using them. The Visual Instance 3D class allows getting the scenario instance and instance base via the Visual Instance 3D get instance and Visual Instance 3D get base respectively. Try exploring the nodes and resources you are familiar with and find the functions to obtain the server IDs. It is not advised to control RIDs from objects that already have a node associated. Instead, server functions should always be used for creating and controlling new ones and interacting with the existing ones. Creating a sprite. This is an example of how to create a sprite from code and moving it using the low-level canvas API, canvas item API. Dry mouth from so much talking. Note, when creating canvas items using rendering server, you should reset physics interpolation on the first frame using rendering server canvas item reset physics interpolation. This ensures proper synchronization between the rendering and physics systems. If it is not done, the canvas item may appear to teleport in when the scene is loaded, rather than appearing directly at its intended location. The canvas item API in the server allows you to add draw primitives to it. Once added, they can't be modified. The item needs to be cleared and the primitives re-added. This is not the case for setting the transform, which can be done as many times as desired. Primitives are cleared this way. Instantiating a mesh into 3D space. 3D APIs are different from 2D ones, and so instantiating API must be used. Creating a 2D rigid body and moving a sprite with it. This creates a rigid body 2D using the physics server 2D API and moves a canvas item when the body moves. The 3D version should be very similar, as the 2D and 3D physics servers are identical using rigid body 3D and physics server 3D respectively. Getting data from the servers. Try to never request any information from running server, physics server 2D, or physics server 3D by calling functions unless you know what you are doing. These servers will often run asynchronously for performance, and calling any function that returns a value will stall them and force them to process anything pending until the function is actually called. This will severely decrease performance if you call them every frame, and it won't be obvious why. Because of this, most APIs and such servers are designed so it's not even possible to request information back until its actual data can be saved. CPU optimization, measuring performance. We have to know where the bottlenecks are to know how to speed up our program. Bottlenecks are the slowest parts of the program that limit the rate that everything can progress. Focusing on bottlenecks allows us to concentrate our efforts on optimizing these areas, which will give us the greatest speed improvement, instead of spending a lot of time optimizing functions that will lead to small performance improvements. For the CPU, the easiest way to identify bottlenecks is to use the profiler. CPU profilers. Profilers run alongside your program and take timing measurements to work out what proportion of time is spent in each function. The Godot IDE conveniently has a built-in profiler. It does not run every time you start your project. It must be manually started and stopped. This is because, like most profilers, recording these timing measurements can slow down your project significantly. After profiling, you can look back at the results for a frame. Note, we can see the cost of built-in processing, such as physics and audio, as well as seeing the cost of our own scripting functions at the bottom. The time spent waiting for various built-in servers may not be counted in the profilers. This is a known bug. When a project is running slow, you will often see an obvious function or process taking a lot more time than others. This is your primary bottleneck, and you can usually increase speed by optimizing this area. For more info about using Godot's built-in profiler, see Debugger panel. External profilers. Although the Godot IDE profiler is very convenient and useful, sometimes you need more power and the ability to profile the Godot Engine source code itself. You can use a number of third-party C++ profilers to do this. From the left, call grind is listing the percentage of time within a function and its children, inclusive, the percentage of time spent within the function itself, excluding child function self, the number of times the function is called, the function name, and the file or module. In this example, we can see nearly all the time is spent under main iteration function. This is the master function in the Godot source code that is called repeatedly. It causes frames to be drawn, physics ticks to be simulated, and nodes to be scripted to be updated. A proportion of the time is spent in the functions to render a canvas. 66% because this example uses a 2D benchmark. Below this we see that almost 50% of the time is spent outside Godot code in libglapi and I965DRI, the graphics driver. This tells us the large proportion of CPU time is being spent in the graphics driver. This is actually an excellent example because in an ideal world, only a very small proportion of time would be spent in the graphics driver. This is an indication that there's a problem with too much communication and work being done in the graphics API. This specific profiling led to the development of 2D batching, which greatly speeds up 2D rendering by reducing bottlenecks in this area. Manually timing functions. Another handy technique, especially once you have identified the bottleneck using a profiler, is to manually time the function or area under test. The specifics vary depending on the language, but in GDScript you would do the following. When manually timing functions, it is usually a good idea to run the function many times, 1,000 or more times, instead of just once, unless it is a very slow function. The reason for doing this is that timers often have limited accuracy. Moreover, CPUs will schedule processing in a haphazard manner. Therefore, an average over a series of runs is more accurate than a single measurement. As you attempt to optimize functions, be sure to either repeatedly profile or time them as you go. This will give you crucial feedback as to whether the optimization is working or not. Caches. CPU caches are something else to be particularly aware of, especially when comparing timing results of two different versions of a function. The results can be highly dependent on whether the data in the CPU cache or not. The data is in the CPU cache or not. CPUs don't load data directly from the system RAM, even though it's huge in comparison to the CPU cache, several gigabytes instead of instead of a few megabytes. This is because system RAM is very slow to access. Instead of CPUs load data from a smaller, faster bank of memory called cache. Loading data from cache is very fast, but every time you try and load a memory address that is not stored in cache, the cache must make a trip to main memory and slowly load in some data. This delay can result in the CPU sitting around idle for a long time, and is referred to as cache miss. This means that the first time you run a function, it may run slowly because the data is not in the CPU cache. The second and later times, it may run much faster because the data is in the cache. Due to this, always use averages when timing, and be aware of the effects of cache. Understanding caching is also crucial to CPU optimization. If you have an algorithm routine that loads small bits of data from randomly spread out areas of main memory, this can result in a lot of cache misses. A lot of time, the CPU will be waiting around for data instead of doing any work. Instead, if you can make your data accesses localized, or even better, accessing memory in a linear fashion, like a continuous list, then the cache will work optimally and the CPU will be able to work as fast as possible. Godot usually takes care of such low-level details for you. For example, the server APIs must be sure data is optimized for caching already for things like rendering and physics. Still, you should be especially aware of caching when writing GD extensions. Languages. Godot supports a number of different languages, it is worth bearing in mind that there are trade-offs involved. Some languages are designed for ease of use at the cost of speed, and others are faster but more difficult to work with. Built-in engine functions run at the same speed regardless of the scripting language you choose. If your project is making a lot of calculations in its own code, consider moving those calculations to a faster language. GDScript. GDScript is designed to be easy to use and iterate, and is ideal for making many types of games. However, in this language, ease of use is considered more important than performance. If you need to make heavy calculations, consider moving some of your project to one of the other languages. C#. C# is popular and has first-class support in Godot. It offers a good compromise between speed and ease of use. Beware of possible garbage collection pauses and leaks that can occur during gameplay. Though, a common approach to work around issues with garbage collection is to use object pooling, which is outside the scope of this guide. Other languages. Third parties provide support for several other languages, including Rust. C++. Godot is written in C++. Using C++ will usually result in the fastest code. However, on a practical level, it is almost difficult to deploy to end users' machines on different platforms. Options for using C++ include GD extensions and custom modules. Threads. Consider using threads when making a lot of calculations that can run in parallel to each other. Modern CPUs have multiple cores, each one capable of doing a limited amount of work. By spreading work over multiple threads, you can move further towards peak CPU efficiency. The disadvantage of threads is that you have to be incredibly careful, as each CPU core operates independently. They can end up trying to access the same memory at the same time. One thread can be reading to a variable while another is writing. This is called race condition. Before you use threads, make sure you understand the dangers of how you can try to prevent these race conditions. Threads can make debugging considerably more difficult. For more information on threads, see using multiple threads. Scene tree. Although nodes are an incredibly powerful and versatile concept, be aware that every node has a cost built in functions, such as process and physics process. Propagate through the tree. This housekeeping can reduce performance when you have a very large number of nodes. How many exactly depends on the target platform, and can range from thousands of tens of thousands, so ensure that you profile performance on all target platforms during development. Each node is handled individually in the Godot renderer. Therefore, a smaller number of nodes with more in each can lead to better performance. One quirk of the scene tree is that you can sometimes get much better performance by removing nodes from the scene tree, rather than by pausing or hiding them. You don't have to delete a detached node. You can For example, keep a reference to a node, detach it from the scene tree using node remove child node, then reattach it later using node add child node. This can be very useful for adding and removing areas from a game, for example. You can avoid the scene tree altogether by using server APIs. For more information, see optimization using servers. Physics. In some situations, physics can end up becoming a bottleneck. This is particularly the case with complex worlds and large numbers of physics objects. Here are some techniques to speed up physics. Try using simplified versions of your rendered geometry for collision shapes. Often this won't be noticeable for end users, but can greatly increase performance. Try removing objects from physics when they are out of view or outside the current area, or reusing physics objects Maybe you allow 8 monsters per area, for example, and reuse these. Another crucial aspect to physics is the physics tick rate. In some games, you can greatly reduce the tick rate, and instead of, for example, updating physics 60 times per second, you may update them only 30 or 20 times per second. This can greatly reduce the CPU load. The downside of changing physics tick rate is you can get jerky movement or jitter when the physics update rate does not match the physics frames per second rendered. Also, decreasing the physics tick rate will increase input lag. It's recommended to stick to the default physics tick rate, 60 Hz, in most games that feature real-time player movement. The solution to jitter is to use fixed time-step interpolation, which involves smoothing the rendered positions and rotations over multiple frames to match the physics. Godot has built-in physics interpolation, which you can read about here. Performance-wise, interpolation is a very cheap operation compared to running a physics tick. It's orders of magnitude faster, so this can be a significant performance win while also reducing jitter. GPU optimization. Introduction. The demand for new graphics features and progress almost guarantees that you will encounter graphics bottlenecks. Some of these can be on the CPU side, but for instance, in calculations inside the Godot engine to prepare objects for rendering. Bottlenecks can also occur on the CPU in the graphics driver, which sorts instructions to pass to the GPU, and in the transfer of these instructions. And finally, bottlenecks also occur on the GPU itself. Where bottlenecks occur in rendering is highly hardware specific. Mobile GPUs in particular may struggle with scenes that run easily on desktop. Understanding and investigating GPU bottlenecks is slightly different to the situation on the CPU. This is because often you can only change performance directly by changing the instructions you give to the GPU. Also, it may be more difficult to make measurements in many cases. The only way of measuring performance is by examining changes in the time spent rendering each frame. Draw calls, state changes, and APIs. Note, the following section is not relevant to end users, but is useful to provide background information that is relevant in later sections. Godot sends instructions to the GPU via a graphics API, Vulkan, OpenGL, OpenGL-ES, or WebGL. The communication and driver activity involved can be quite costly, especially OpenGL, OpenGL-ES, and WebGL. If we can provide these instructions in a way that is preferred by the driver and GPU, we can greatly increase performance. Nearly every API command in OpenGL requires a certain amount of validation to make sure the GPU is in the correct state. Even seemingly simple commands can lead to a flurry of behind-the-scenes housekeeping. Therefore, the goal is to reduce these instructions to a bare minimum and group together similar objects as much as possible so they can be rendered together, or with the minimum number of these expensive state changes. 2D batching. In 2D, the cost of treating each item individually can be prohibitively high. There can easily be thousands of them on the screen. This is why 2D batching is used. Multiple similar items are grouped together and rendered in a batch via a single draw call, rather than matching a separate draw call for each item. In addition, this means state changes, material, and texture changes can be kept at a minimum. Don't need to worry about 3D batching. Reuse shaders and materials. The Godot renderer is a little different to what is out there. It's designed to minimize GPU state changes as much as possible. Standard Material 3D does a good job at reusing materials that need similar shaders. If custom shaders are used, make sure to reuse them as much as possible. Godot's priorities are reusing materials. The fewer different materials in the scene, the faster the rendering will be. If a scene has a huge amount of objects in the rendered in the hundreds or thousands, try reusing the materials in the worst case. In the worst case, the atlases to decrease the amount of texture changes. Reusing shaders. If materials can't be reused, at least try to reuse shaders. Note, shaders are automatically reused between standard material 3Ds that share the same configuration. Features that are enabled or disabled with a checkbox, even if they have different parameters. If a scene has, for example, 20,000 objects with 20,000 different materials each, rendering will be slow. If the same scene has 20,000 objects but only 100 materials, rendering will be much faster. Pixel cost versus vertex cost. You may have heard that the lower number of polygons in a model, the faster it will be rendered. This is really relative and depends on many factors. On modern PC and console, vertex cost is low. GPUs originally only rendered triangles. This meant that every frame, all vertices had to be transformed by the CPU, including clipping. All vertices had to be sent to the GPU memory from the main RAM. Nowadays, all this is handled inside the GPU, greatly increasing performance. 3D artists usually have the wrong feeling about poly count performance because 3D modeling software such as Blender, 3ds Max, etc. need to keep geometry in CPU memory for it to be edited, reducing actual performance. Game engines rely on the GPU more, so they can render many triangles much more efficiently. On mobile devices, the story is different. PC and console GPUs are brute force monsters that can pull as much electricity as they need from the power grid. Mobile GPUs are limited to a tiny battery, so they need to be a lot more power efficient. To be more efficient, mobile GPUs attempt to avoid overdraw. Overdraw occurs when the same pixel on the screen is being rendered more than once. Imagine a town with several buildings. GPUs don't know what is visible and what is hidden until they draw it. For example, a house might be drawn and then another house in front of it, which means rendering happens twice for the same pixel. PC GPUs normally don't care much about this and just throw more pixel processors to the hardware to increase performance, which also increases power consumption. Using more power is not an option on mobile, so mobile devices use a technique called tile-based rendering, which divides the screen into a grid. Each cell keeps a list of triangles drawn to it and sorts them by depth and to minimize overdraw. This technique improves performance and reduces power consumption, but takes a toll on vertex performance. As a result, fewer vertices and triangles can be processed for drawing. Additionally, tile-based rendering struggles when there are small objects and a lot of geometry within a small portion of the screen. This forces mobile GPUs to put a lot of strain on a single screen tile, which considerably decreases performance as all other cells must wait for it to complete before displaying the frame. To summarize, don't worry about vertex count on mobile, but avoid concentration of vertices in small parts of the screen. If a character, NPC, vehicle, etc. is far away, which means it looks tiny, use a smaller level of detail LOD model. Even on desktop GPUs, it's preferable to avoid having triangles smaller than the size of a pixel on screen. Pay attention to the additional vertex processing required when using skinning, skeletal animation, morphs, shape keys, vertex, lit objects common on mobile. Pixel fragment shaders and fill rate. In contrast to vertex processing, the costs of fragment per pixel shading have increased dramatically over the years. Screen resolutions have increased. The area of 4K screen is 8,294,400 pixels versus 307,200 for an old 6040 by 480 VGA screen. That is 27 times the area. Also, the complexity of fragment shaders has exploded. Physically based rendering requires complex calculations for each fragment. You can test whether a project is fill rate limited quite easily. Turn off VSync to prevent capping the frames per second. Then compare the frames per second when running with a large window to running with a very small window. You may also benefit very similarly reducing your shadow map size if using shadows. Usually you will find the FPS increases quite a bit using a small window, which indicates you are to some extent fill rate limited. On the other hand, if there is little to no increase in FPS, then your bottleneck lies elsewhere. You can increase performance in a fill rate limited project by reducing the amount of work the GPU has to do. You can do this by simplifying the shader, perhaps turn off expensive options if you are using a standard Material 3D, or reducing the number and size of textures used. Also, when using shaded particles, consider forcing vertex shading in their material to decrease the shading cost. See also, unsupported hardware, variable rate shading can be used to reduce shading processing costs without impacting the sharpness of edges on the final image. When targeting mobile devices, consider using the simplest possible shaders you can reasonably afford to use. Reading textures. The other factor in fragment shaders is the cost of reading textures. Reading textures is an expensive operation, especially when reading from several textures in a single fragment shader. Also consider that filtering may slow it down further. Try linear filtering between mipmaps and averaging. Reading textures is also expensive in terms of power usage, which is a big issue on mobiles. If you use third-party shaders or write your own shaders, try using algorithms that require as few texture reads as possible. Texture compression. By default, Godot compresses textures of 3D models when importing using VRAM compression. Video RAM compression isn't as efficient in size as PNG or JPEG when stored, but increases performance enormously when drawing large enough textures. This is because the main goal of texture compression is bandwidth reduction between memory and the GPU. In 3D, the shapes of objects depend more on the geometry than the texture, so compression is generally noticeable. In 2D, compression depends more on shapes inside the textures, so the artifacts resulting from 2D compression are more noticeable. As a warning, most Android devices do not support texture compression of textures with transparency, only opaque, so keep this in mind. Note, even in 3D, pixel art textures should have VRAM compression disabled, as it will negatively affect their appearance, without improving performance significantly due to their low resolution. Post-processing and shadows. Post-processing effects and shadows can also be expensive in terms of fragment shading activity. Always test the impact of these on different hardware. Reducing the size of shadow maps can increase performance, both in terms of writing and reading the shadow maps. On top of that, the best way to improve performance of shadows is to turn shadows off for as many lights and objects as possible. Smaller or distant omni lights, spotlights, can often have their shadows disabled with only a small visual impact. Transparency and blending. Transparent objects present particular problems for rendering efficiency. Opaque objects, especially in 3D, can be essentially rendered in any order, and the Z buffer will ensure that only the frontmost objects get shaded. Transparent or blended objects are different. In most cases, they cannot rely on the Z buffer and must be rendered in painter's order, i.e. from back to front to look correct. Transparent objects are also particularly bad for fill rate, because every item has to be drawn even if other transparent objects will be drawn on top later on. Opaque objects don't have to do this. They can usually take advantage of the Z buffer by writing to the buffer only first. When only performing the fragment shader on the winning fragment, the object that is at the front at a particular pixel. Transparency is particularly expensive where multiple transparent objects overlap. It is usually better to use transparent areas as small as possible to minimize these fill rate requirements, especially on mobile, where fill rate is very expensive. Indeed, in many situations, rendering more complex opaque geometry can end up being faster than using transparency to cheat. Multi-platform device. If you're aiming to release on multiple platforms, test early and test often on all your platforms, especially mobile. Developing a game on desktop can be attempted to port, but attempting to port it to mobile at the last minute is a recipe for disaster. In general, you should design your game for the lowest common denominator, then add optional enhancements for more powerful platforms. For example, you may want to use the compatibility rendering method for both desktop and mobile platforms where you target both. Mobile tiled renderers. As described above, GPUs on mobile devices work in dramatically different ways from GPUs on desktop. Most mobile devices use tile renderers. Tile renderers split up the screen into regular sized tiles that fit into super fast cache memory, which reduces the number of read or write operations to the main memory. There are some downsides though. Tiled rendering can makes certain techniques much more complicated and expensive to perform. Tiles that rely on the results of rendering and different tiles on the results of early operations being preserved can be very slow. Be very careful to test the performance of shaders, viewport, textures, and post-processing. Oh shit, that was just for that. Damn. Okay. I need to use the bathroom again. I'll be back. Alright, I'm back. 2.5 hours, huh? Work in progress. Alright, optimization using multi-meshes. For large amount of instances in the thousands that need to be constantly processed and certain amount of control needs to be retained, using servers directly is a recommended optimization. When the amount of objects reach the hundreds of thousands or millions, none of these approaches are efficient anymore. Still, depending on the requirements, there is one more optimization available. Multi-meshes. A multi-mesh is a single draw primitive that can draw up to millions of objects in one go. It's extremely efficient because it uses the GPU hardware to do this. The only drawback is there is no screen or frustum culling process for individual instances. This means that millions of objects will be always or never drawn, depending on the visibility of the whole multi-mesh. It is possible to provide a custom visibility rect for them, but it will always be all or none visibility. If the objects are simple enough, just a couple of vertices, this is generally not much of a problem, as most modern GPUs are optimized for this use case. A workaround is to create several multi-meshes for different areas of the world. It is also possible to execute some logic inside the vertex shader using the instance ID or instance custom built-in constants for an example of animating thousands of objects in a multi-mesh. See the animating thousands of fish tutorial. Information to the shader can be provided via textures. There are floating point image formats which are ideal for this. Another alternative is to use a GDE extension in C++, which should be extremely efficient. It's possible to set the entire state for all objects using linear memory via the rendering server multi-mesh set buffer function. This way, the array can be created using multiple threads, then set in one call, providing high cache efficiency. Finally, it's not required to have all multi-mesh instances visible. The amount of visible ones can be controlled with the multi-mesh visible instance count property. This typical workflow is to allocate the maximum amount of instances that will be used, then change the amount visible depending on how many are currently needed. Multi-mesh example. Here's an example of using a multi-mesh from code. Languages other than GDScript may be more efficient for millions of objects, but for a few thousands, GDScript should be fine. Bella! Bella, where's that Shelby? That sounds like Bella. Bella! Hello, Bella. Hi, how are you? Is Zach up here? Is that why you're here? Okay. Reducing shutter from shader pipeline compilations. Warning, this page only applies to the Ford Plus and mobile renders. Not compatibility Uber shaders and pipeline pre-compilation rely on functionality only available in modern low-level graphics APIs, Vulkan, blah blah blah. Pipeline compilation, also commonly known as shader compilation, is an expensive operation required by the engine to be able to draw any kind of content with the GPU. In more precise terms, shader compilation involves the translation of the GLSL code that Godot generates into an intermediate format that can be shared across systems, such as SPIRV when using Vulkan. However, this format can't be used by the GPU directly. Pipeline compilation is the step where the GPU driver converts intermediate shader format, the result from shader compilation, to something the GPU can actually use for rendering. Drivers usually keep a cache of pipelines stored somewhere in the system to avoid repeating the process every time a game is run. This cache is usually deleted when the driver is updated. Pipelines contain more information than just the shader code, which means that for each shader there can be dozens of pipelines or more. This makes it difficult for an engine to compile them ahead of time, both because it would be very slow and because it would take up a lot of memory. On top of that, this step can only be performed on the user's system and is very tough to share the result between users unless they have the exact same hardware and driver version. Before Godot 4.4, there was no solution to pipeline compilation other than generating them when an object shows up inside the camera's view, leading to the infamous shader stutter or hitches that only occur during the first playthrough. Oh, shut up. I'm not talking to you. Ugh. You know what? I'm gonna take that as a compliment. I don't care if you meant it as an insult. I'm going to take it as a compliment. Because, Smarts, does a lot of things in life for you. But how are you, Hergeslurgan Company? I need to do something. I'll pull this over here. Actually, no, I don't need to. Pull it over there. All I need to do is go here. It was... Okay, okay. Or it was an insult or was a compliment? It was in fact a compliment. Okay. No, wait. Go back. View and live control room. Oh, fuck. Come on. All I need... I just need the chat. Stream settings, stream health. Yeah, it's fine. But what about the chat? Dashboard, channel level settings, something back. Maybe let's try refreshing it. Hey buddy, who do you think the guy running this... Who do you think is the guy running this account?
It's me.
Yeah, I figured it was you. What the fuck? Where the hell? Why
Trying to
is...
figure out how you make people mods.
Yeah, but like chat isn't showing up, so I can't. I can't.
You can't?
I can't. Yeah, it's weird. Maybe if I go here and then try switching my account, because, if I go here, then it'll just be on my own personal account. What the hell? Why can't I see chat? Chat rate, concurrent viewers, views too. Do you know why this is happening?
I don't. I've literally never streamed with YouTube before.
Maybe manage pop-out dashboard. Maybe this will work? I'm gonna drag it over here. No, I don't need to switch account. It's like stream, refresh page, account. No, not any of that. What the fuck? No. Interesting. I don't know what to do about that. Maybe I can change it. Maybe I can manage it in Streamlabs?
Maybe, I don't know.
Nothing's happening when I click shit in here. Participants.
Have you logged into the account in the chat box? Because that's a thing Streamlabs needs you to do.
It says sign into chat, but then it takes me to open in web browser, and then I'm signed in on my personal account.
Huh. Weird.
Maybe I can just do it in settings. Somewhere, stream, output. Search, let's see. Chat? Chat settings. Oh, that just switches its side. And I am logged in to Hergesbergen Games on Streamlabs. So that's not it. Maybe? Now that's... Here, let me show you. Okay, so when I try to click on it, nothing happens.
You watching it.
Yeah. Yeah, if I click on profile, nothing happens. If I try right-clicking, nothing happens. If I click on the dots, nothing happens.
Maybe you do need to sign in the chat first.
How?
I don't know.
Oh, what do you mean? Oh, that's my personal account. Boop. Okay, now I go back. And there we go. Add as moderator. Managing moderator. Yes.
Okay.
And now we're gonna add myself as a moderator, because why not? Ooga booga. And then I go over here and managing moderator. Bleh. Alright, what the hell? Why'd the music stop? Oh, refresh Google account. Dumb.
I'm actively editing the playlist.
Oh, I have my own personal edited version, but yeah, I'll take a look at it. But what you can do is collaboration with it, so that I can also change things with it. But we can worry about that later. Right now, I'm doing shit.
No, you're not.
As you may be very well aware. So, do you know when you'll hear back from Walmart on that job application? Or on that interview?
Like a couple days.
A couple days. Alright, alright. Okay. I forgot where I left off reading. Oh well. Pipelines contain more information than... Nah, you're fine. Than just the shader cache, which means that that for each shader, there can be dozens of pipelines or more. This makes it difficult for an engine to compile them ahead of time, both because it would be very slow and because it would take up a lot of memory. On top of that, this step can only be performed performed on the user's system, and it is very tough to share the result between users, unless they have the exact same hardware and driver version. Before Godot 4.4, there was no solution to pipeline compilation other than generating them when an object shows up inside the camera's view, leading to infamous shader stutter or hitches that only occur during the first playthrough. With Godot 4.4, new mechanisms have been introduced to mitigate stutters from pipeline compilation. Uber shaders. Godot makes use of specialization constants and a feature that allows the driver to optimize a pipeline's code around a set of parameters such as lighting, shadow quality, etc. Specialization constants are used to optimize a shader by limiting unnecessary features. Changing a specialization constant requires recompiling the pipeline. Uber shaders are a special version of the shader that are able to change these constants while rendering, which means Godot can recompile just one pipeline instead of ahead of time and compile the more optimized version on the background during gameplay. This reduces the amount of pipelines that need to be created significantly. Pipeline pre-compilation. By using Uber shaders, the engine can recompile pipelines ahead of time in multiple places, such as when meshes are loaded or when nodes are added to the scene. By being part of the resource loading process, pipelines can even be recompiled in multiple background threads if possible during loading screens or even gameplay. Starting in Godot 4.4, Godot will detect which pipelines are needed and precompile them at load time. This detection system is mostly automatic, but it relies on the rendering server seeing evidence of all shaders, meshes, or rendering features at load time. For example, if you load a mesh and a shader while the game is running, the pipeline for that mesh shader combination won't be compiled until the mesh shader is loaded. Similarly, things like enabling MSAA or instancing a voxel GI node while the game is running will trigger pipeline recompilations. Oh, you want to see? Oh, he's deafened. All right. Pipeline pre-compilation monitors. Compiling pipelines ahead of time is the main mechanism Godot uses to mitigate shader stutters, but it's not a perfect solution. Being aware of situations that can lead to pipeline stutters can be very helpful, and the workarounds are pretty straightforward compared to previous versions. These workarounds may be less necessary over time with the future versions of Godot as more detection techniques are implemented. The Godot debugger often monitors for tracking the amount of pipelines created by the game and the step that triggered their compilation. You can keep an eye on these monitors as the game runs to identify potential sources of shader stutters without having to wipe your driver cache every time you wish to test sudden increases of these values outside of loading screens can show up as hitches during a gameplay the first time someone plays the game on their system. It is recommended you take a look at these monitors to identify possible sources of stutter for your players, as you might be unable to experience them yourself without deleting your driver cache or testing on a weaker system. Note, we can see the pipelines compiled during gameplay and verify which steps could possibly cause stutters. Note that these values will only increase and never go down, as deleted pipelines are not tracked by these monitors, and pipelines may be erased and created during gameplay. Canvas, compiled when drawing a 2D node. The engine does not currently feature pre-compilation for 2D elements, and stutters will show up when the 2D node is drawn for the first time. Mesh, compiled as part of loading a 3D mesh and identifying what pipelines can be pre-compiled from its properties. These can lead to stutters if a mesh is loaded during gameplay, but they can be mitigated if the mesh is loaded by using a background thread. Modifiers that are part of nodes, such as material overrides, can't be compiled on this step. Surface, compiled when a frame is about to be drawn and 3D objects are instanced on the scene tree for the first time. This can also be This can also include compilation for nodes that aren't even visible on the scene tree. The stutter will occur only on the first frame the node is added to the scene, which won't result in an obvious stutter if it happens right after a loading screen. Draw, compiled on demand when a 3D object needs to be drawn and an Uber shader was not pre-compiled ahead of time. The engine is unable to pre-compile this pipeline due to triggering a case that hasn't been covered yet, or a modification that was done to the engine's code leads to stutters during gameplay. This is identical to Godot versions before 4.4 if you can see compilations here. Please let the developers know, as this should never happen with the Uber shader system. Make sure to attach a minimal reproduction project when doing so. Specialization, compiled in the background during gameplay to optimize the frame rate, unable to cause stutters but may result in reduced frame rates if there are many happening per frame. Pipeline pre-compilation features. Godot offers a lot of rendering features that are not necessarily used by every frame. Unfortunately, pipeline pre-compilation can't know ahead of time if a particular feature is used by a project. Some of these features can be detected when a user adds a node to the scene or toggles a particular setting in the project or the movement or the environment. The pipeline pre-compilation system will keep track of these features as they're encountered for the first time and enable pre-compilation of them for any meshes or surfaces that are created afterwards. Ethan, you know what's fun?
What?
The amount of progress I've gotten through on the manual section of the Godot Engine documentation.
What have you gotten?
For manual, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 different sections for manual. And I've gone through 16 and the one I'm doing currently.
Nice, nice.
Yeah, but there are also 3 sections after manual: the engine details, community, which I probably won't need to look at, and class reference, which I will probably look at. Engine details, I don't know how much of that I'll read, but community I definitely won't. What were you playing?
Huh?
What were you playing?
Risk of Rain. I just forgot to open it with mods.
Ah, good job. If your game
Stupid idiot.
If your game makes use of these features, make sure to have a scene that uses them as early as possible before loading the majority of the assets. This scene can be very simple and will do the job as long as it uses the features the game plans to use. It can be rendered off screen for at least 1 frame if necessary, example by covering it with a color rect node or by using sub-viewport located outside the window bounds. You should also keep in mind the changing of any features during gameplay will result in immediate stutters, making sure to only change these features from configuration screens if necessary, and insert loading screens and messages when the game changes are applied. MSA level enabled. MSAA level. Enabled when the level of 3D MSAA is changed on the project settings. Unfortunately, different MSAA levels being used on different viewports will lead to stutters as the engine only keeps track of 1 level at a time to perform pre-compilation. Reflection probes. Enabled when a reflection probe node is placed on the screen. Separate specular. Enabled when using effects like surface scattering or a compositor effect that relies on sampling the specularity directly off the screen. Motion vectors. Enabled when using effects such as TAA, FSR2, or compositor effect that requires motion vectors, such as motion blur. Normal and roughness, enabled when using SDFGI, voxel GI, screen space reflections, SSAO, SSIL, or using the normal roughness buffer in a custom shader or compositor effect. Light maps enabled when a light map GI node is placed on the scene and a node uses a baked light map. Voxel GI enabled when a voxel GI node is placed on the scene. SDFGI enabled when the world environment enables SDFGI. Multiview enabled for XR projects. 1632-bit Windows enabled when the configuration of the depth precision of shadow maps is changed on the project settings. Omni Shadow Dual Paraboloid, enabled when an Omni light casts shadows and uses the dual paraboloid mode. Omni Shadow Cube Map, enabled when an Omni light casts shadows and uses the cube map mode, which is the default. If you witness stutters during gameplay and the monitors report a sudden increase in compilations during the surface step, it is very likely a feature was not enabled ahead of time. Ensuring that this effect is enabled while loading your game will likely mitigate the issue. Pipeline pre-compilation instancing. One common source of stuttering games is the fact that some effects are only instanced on the scene because of interactions that only happen during gameplay. For example, if you have a particle effect that is only added to the scene through a script when a player doesn't action, even if the scene is preloaded, the engine might be unable to precompile the pipelines until the effect is added to the scene at least once. Luckily, it's possible for Godot 4.4 and later to precompile these pipelines as long as the scene is instantiated at least once on the scene, even if it's completely invisible or outside of the camera's view. Hidden bullet node attached to the player in one of the demo projects. This helps the engine precompile the effects pipeline ahead of time. If you're aware of any effects that are added to the scene dynamically during gameplay, and you are seeing sudden increases on the compilations monitor when these effects show up, a workaround is to attach a hidden version of the effect somewhere that is guaranteed to show up. For example, if the player character is able to cause some sort of explosion, you can attach the effect as a child of the player as an invisible node. Make sure to disable the script attached to the hidden node or to hide any other nodes that could cause issues, which can be done by enabling editable children on the node. Shader Baker. Since Godot 4.5, you can choose to bake shaders on export to improve initial startup time. This will generally not resolve existing stutters, but it will reduce the time it takes to load the game for the first time. This is especially the case when using Direct3D, 12, or Metal, which have significantly slower initial shader compilation times than Vulkan due to the conversion step required. Godot's own shaders use GLSL and SPIR-V, but Direct3D, 12, and Metal use different formats. Note, the shader baker can only make the source into the intermediate format, SPIR-V for Vulkan, DXIL for Direct3D 12, MIL for Metal. It cannot bake the intermediate format into the final pipeline, as this is dependent on the GPU driver and the hardware. The shader baker is not the replacement for the pipeline pre-compilation, but it aims to complement it. When enabled, the shader baker will bundle compiled shader code into the PCK, which results in the shader compilation step being skipped entirely. The downside is that exporting will take slightly longer. The PCK file will be larger by a few megabytes. A shader baker is disabled by default, but you can enable it in each export preset in the export dialog by ticking the shader baker enabled export port option. Note that shader baking will only be able to export shaders for drivers supported by the platform the editor is currently running on. The editor running on Windows can support shaders for Vulkan and Direct3D 12. Don't need to worry about anything else because I'm only working in the Windows. The shader baker will only export shaders that match the rendering device driver project setting for the target platform. Note, the shader baker is only supported for the Forward Plus and mobile renderers. It will have no effect if the project uses the compatibility renderer, or for users who make use of the compatibility fallback due to their hardware not supporting the Forward Plus or mobile renderer. This also means the shader baker is not supported on the web platform, as the web platform only supports the compatibility renderer. Don't need to worry about 3D. Threads. Performance, introduction. Wait, no, I want threads. No, threads. Using multiple threads. See also for a list of multi-threading primitives in C++, see multi-threading or concurrency. Threads allow simultaneous execution of code. It allows offloading work for the main thread. Godot supports threads and provides many handy functions to use them. Note, if using other languages, C#, C++, it may be easier to use the threading classes they support. Warning, before using a built-in class in a thread, read thread-safe APIs first to check whether it can be safely used in a thread. Creating a thread. To create a thread, use the following code. Your function will then run in a separate thread until it returns, even if the function is already returned. The thread must collect it, so call thread wait to finish, which will wait until the thread is done, if not done yet. When then properly dispose of it. Warning, creating threads is a slow option, especially on Windows. To avoid unnecessary performance overhead, make sure to create threads overhead by processing before heavy processing is needed instead of creating threads just in time. For example, if you need multiple threads during gameplay, you can create threads while the level is loading and only actually start processing with them later on. Additionally, locking and unlocking of mutexes can also be an expensive operation. Locking should be done carefully. Avoid locking too often or for too long. Mutexes. Accessing objects or data from multiple threads is not always supported. If you do it, it will cause unexpected behaviors or crashes. Read the thread-safe API's documentation to understand which engine APIs support multiple thread access. When processing your own data or calling your own functions, as a rule, try to avoid processing the same data directly from different threads. You may run into synchronization problems, as the data is not always updated between CPU cores when modified. Always use a mutex when processing a piece of data from different threads. When calling mutex lock, a thread ensures that all other threads will be blocked. Put on suspended state if they try to lock the same mutex. When the mutex is unlocked by calling mutex unlock, the other threads will be allowed to process with lock, but only one at a time. Here's an example of using a mutex. Semaphores. Sometimes you want your thread to work on demand. In other words, tell it when to work and let it suspend when it isn't doing anything. For this, semaphores are used. The function semaphore wait is used in the thread to suspend it until some data arrives. The main thread instead uses semaphore post to signal that data is ready to be processed. Thread-safe APIs. Threads. Threads are used to balance processing power across CPUs and cores. Godot supports multi-threading, but not in the whole engine. Below is a list of ways multi-threading can be used in different areas of Godot. Global scope. Most global scope singletons are thread-safe by default. Accessing servers from threads is supported. However, for the rendering and physics servers, thread-safe operation must be enabled in the project settings first. This makes singletons ideal for code that creates dozens of thousands of instances in servers and controls them from threads. Of course, it requires a bit more code, and this is used directly and not within the scene tree. Scene tree. Interacting with the active scene tree is not thread safe. Make sure to use mutexes when sending data between threads. If you want to call functions or set properties from a thread, you may use call deferred or set deferred. However, creating scene chunks nodes in tree arrangement outside the active tree is fine. This way, parts of a scene can be built or instantiated in a thread, then added in the main thread. Still, this is only really useful if you have one thread loading data. Attempting to load or create scene chunks from multiple threads may work, but you risk resources, which are only loaded once in Godot, being tweaked by the multiple threads, resulting in unexpected behaviors or crashes. Only use more than one thread to generate scene data if you really know what you are doing and you are sure that a single resource is not being used or set in multiple ones. Otherwise, you are safer just using the server APIs, which is fully thread safe, directly and not touching scene or resources. Rendering. Instancing nodes that render anything in 2D or 3D, such as Sprite 2D or Mesh Instance 3D, is not thread safe. Is not thread safe by default. To run the rendering driver on a separate thread, set the rendering driver thread model project setting to separate. Note that the separate thread model has several known bugs, so it may not be usable in all scenarios. Warning: you should avoid calling functions involving direct interaction with the GPU on other threads, such as creating new textures or modifying and retrieving image data. These operations can lead to performance stalls because they require synchronization with the rendering server, as data needs to be transmitted to or updated on the GPU. Physics. Physics simulation is not thread safe by default. To run the physics servers on separate threads, making them thread safe, enable the following project settings: Physics Server 2D, Physics 2D run on separate thread. Navigation. Navigation Server 2D and Navigation Server 3D are both thread safe and thread friendly. The navigation related query functions can be called by threads and run in true parallel. By default, a conservative number of threads is supported running in true parallel on navigation maps before additional threads have to wait for map data access at a semaphore. To increase the number of threads that can be run simultaneously on map data, see Navigation Pathfinding Max Threads. The navigation server related resources like navigation source geometry data, navigation mesh, and navigation polygon are all thread safe but not necessarily thread friendly. They use internal read-write locks for thread safety, so editing the same resource, example a single big nav mesh, on multiple threads at the same time can cause thread congestion. The navigation-related helper classes like A*2D, A*3D, and A*Grid 2D are not thread safe. They can be used with threads to some limited capacity, but using two or more threads on the same A* object causes corruption. For example, using a dedicated background thread per A* object to population points or do queries works, but two threads using the same A* object would corrupt each other's data. GDScript arrays and dictionaries. In GDScript, reading and writing elements from multiple threads is okay, but anything that changes the container size, resizing, adding, or removing elements requires locking a mutex. Resources. Modifying a unique resource for multiple threads is not supported. However, handling references on multiple threads is supported. Hence, loading resources on a thread is as well. Scenes, textures, meshes, etc. can be loaded and manipulated on a thread and then added to the active scene on the main thread. The limitation here is as described above. One must be careful not to load the same resource from multiple threads at once. Therefore, it's easiest to use one thread for loading and modifying resources, and the main thread for adding them. Physics. Yay. Ah, fuck, this one's long. Physics introduction. Fuck. Why does physics have to be long? I don't want it to be long. Oh well.
It's because it's physics. There's a lot to it.
In game development,
Okay.
In game development, you often need to know when two objects in the game intersect or come into contact. This is known as collision detection. When a collision is detected, you typically want something to happen. This is known as collision response. Godot offers a number of collision objects in 2D and 3D to provide both collision detection and response. Trying to decide which one to use for your project can be confusing. You can avoid problems and simplify development if you understand how each works and what their pros and cons are. In this guide, you will learn Godot's 4 collision object types, how each collision object works, when and why to choose one type over another. Note, this document's examples will use 2D objects. Every 2D physics object and collision shape has a direct equivalent in 3D, and in most cases they work in much the same way. Collision objects. Godot offers 4 kinds of collision objects which all extend collision object 2D. The last 3 lines below are physics bodies and additionally extended physics body 2D. Area 2D. Area 2D nodes provides detection and influence. They can detect when objects overlap and can emit signals when bodies enter or exit. And Area 2D can also be used to override physics properties, such as gravity or damping, in a defined area. Static body 2D. A static body is one that is not moved by the physics engine. It participates in collision detection, but does not move in response to the collision. They are most often used for objects that are a part of the environment or that do not need to have any dynamic behavior. Rigid body 2D. This is the node that implements simulated 2D physics. You do not control a rigid body 2D directly, but instead you apply forces to it, gravity, impulses, etc. And the physics engine calculates the resulting movement. Read more about using rigid bodies. Character 2D, a body that provides collision detection but not physics. All movement and collision response must be implemented in code. Physics material. Static bodies and rigid bodies can be configured to use a physics material. This allows adjusting to friction and bounce of an object, and set its absorbent and or rough. Collision shapes. A physics body can hold any number of shaped 2D objects as children. These shapes are used to define the object collision bounds and to detect contact with other objects. Note, in order to detect collisions, at least one shape 2D must be assigned to the object. The most common way to assign a shape is by adding a collision 2D or collision polygon 2D as a child of the object. These nodes allow you to draw the shape directly in the editor workspace. Important, be careful never to scale your collision shapes in the editor. The scale property in the inspector should remain 1:1 when changing the shape of the collision shape. You should always use the size handles, not the node 2D scale handles. Scaling a shape can result in unexpected collision behavior. Physics process callback. The physics engine runs at a fixed rate, a default of 60 iterations per second. This rate is typically different from the frame rate, which fluctuates based on what is rendered and available resources. It is important that all physics-related code runs at a fixed rate. Therefore, Godot differentiates between physics and idle processing. Code that runs each frame is called idle processing, and code that runs on each physics tick is called physics processing. Godot provides 2 different callbacks, one for each of those processing rates. The physics callback, node physics process, is called before each physics step. Any code that needs to access a body's properties should be in here. This method will be passed a delta parameter, which is a floating point number equal to the time passed in seconds since the last step when using the default 60 Hz physics update rate. It will typically be equal to 0.016666, but not always. See below. Note, it's recommended to always use the delta parameter when relevant in your physics calculations, so that the game behaves correctly. If you change the physics update rate, or if the player's device can't keep up. Collision layers and masks. One of the most powerful but frequently misunderstood collision features is the collision layer system. This system allows you to build upon complex interactions between a variety of objects. The key concepts are layers and masks. Each collision object 2D has 32 different physics layers it can interact with. Let's take a look at each of the properties in turn. Collision layer. This describes the layers that the object appears in. By default, all bodies are on layer 1. Collision mask. This describes what layers the body will scan for collisions. If an object isn't in one of the mask layers, the body will ignore it. By default, all bodies scan layer 1. These properties can be configured via code or by editing them in the inspector. Keeping track of what you're using each layer for can be difficult, so you can find it useful to assign names to the layers you're using. Names can be assigned in project settings, layered names, 2D physics. GUI example. You have 4 node types in your game: walls, player, enemy, and coin. Both player and enemy should collide with walls. The player node should detect collisions from both enemy and coin, but enemy and coin should ignore each other. Start by naming layers 1 through 4, walls, player, enemies, and coins, and place each node type in its respective layer using the layer property. Then set each node's mask property by selecting the layers it should interact with. For example, the player's setting should look like this. Code example. In function calls, layers are specified as bit mask, where a function enables all layers by default. The layer mask will be given as 0xFFFFFFFF. I have no idea if I read the amount of F's right. Your code can use binary, hexadecimal, or decimal notation for layer masks, depending on your preference. The code equivalent of the above example, where layers 1, 3, and 4 were enabled, would be as follows. You can also set bits independently by calling set collision layer value, layer number value, or set collision mask value, layer number value, on any given collision object 2D as follows. Export annotations can be used to export bit masks in the editor with a user-friendly GUI. Additional export annotations are available for render and navigation layers in both 2D and 3D. See exporting bit flags. Area 2D. Area nodes provide detection and influence. They can detect when objects overlap and emit signals. When bodies enter or exit, areas can also be used to override physics properties, such as gravity or damping, in a defined area. There are 3 main uses for Area 2D: overriding physics parameters, such as gravity, in a given region, detecting when other bodies enter or exit a region, or what bodies are currently in a region, checking other areas for overlap. By default, areas also receive mouse and touchscreen input. Static body 2D. A static body is one that is not moved by the physics engine. It participates in collision detection but does not move in response to the collision. However, it can impart motion or rotation by a colliding object as if it were moving, using its constant linear velocity and constant angular velocity properties. Static body 2D nodes are most often used for objects that are part of the environment or that do not need to have any dynamic behavior. Example uses for static body 2D. Platforms, including moving platforms, conveyor belts, walls, and other obstacles. Rigid body 2D. This is the node that implements simulated 2D physics. You do not control a rigid body 2D directly. Instead, you apply forces to it, and the physics engine calculates the resulting movement, including collisions with other bodies, and collision responses such as bouncing, rotation, etc. You can modify a rigid body's behavior via properties such as mass, friction, or bounce, which can be set in the inspector. The body's behavior is also affected by the world's properties, as set in project settings physics, or by entering an area 2D that is overriding the global physics properties. When a rigid body is at rest and hasn't moved for a while, it goes to sleep. A sleeping body acts like a static body, and its forces are not calculated by the physics engine. The body will wake up when forces are applied, either by a collision or via code. Using rigid body 2D. One of the benefits of using rigid body is that a lot of behavior can be had for free without writing any code. For example, if you were making an Angry Birds style game with falling blocks, you would only need to create rigid body 2Ds and adjust their properties. Stacking, falling, and bouncing would automatically be calculated by the physics engine. However, if you do wish to have some control over the body, you should take care. Altering the position, linear velocity, or other physics properties of a rigid body can result in unexpected behavior. If you need to alter any of the physics related properties, you should use the integrate forces callback instead of physics process. In the callback, in this callback, you have access to the body's physics directed body state 2D, which allows for safely changing properties and synchronizing them with the physics engine. For example, here's a code for an asteroid-style spaceship. Note that we are not setting the linear velocity or angular velocity properties directly, but rather applying forces, thrust, and torque to the body and letting the physics engine calculate the resulting movement. Note, when a rigid body goes to sleep, the integrate forces function will not be called. To overwrite this behavior, you will need to keep the body awake by creating a collision. Applying a force to it, or by disabling the can sleep property. Be aware that this can have a negative effect on performance. Hey, Jesse. Bubble, what are you doing here?
Blah, blah, blah. What are you doing? Well, actually, I know what Wager's doing. What are you doing, Ethan?
Playing Risk of Rain.
I'm doing the same thing.
Whoa, I didn't know that. Totally. I didn't know that both of you were playing Risk of Rain.
Oops. I was genuinely surprised by his statement that he was playing Risk of Rain. I didn't expect it.
Really?
Oh no.
Huh.
It's not something I usually do.
Oh,
At least for the time being.
Jesse, get in. Send a message in the stream real quick. I gotta. Get in here.
Gotta
Set you as moderator. Set you as a moderator. What? That's silly. Well, where's that message?
give me a second.
Right there. On wait, no, that's you. I'm smart.
That's me, yeah.
I can read usernames.
No, you can't.
Yes, I can. I just choose not to.
Ah, I see.
Mmm.
That's not how you spell that.
Oh, shut up, dog.
Where the hell are you streaming? YouTube.
Just go to the Discord and, Discord announcements, and it's, right there, the most recent link. Learning the Godot Engine, episode 5.
I see. Parental, no.
Parental?
Not what I was trying to spell.
Pinar!
Alright.
Pinar!
Yes.
I'm so surprised by this message.
That... Whoa. That's crazy.
So, what are you coding right now?
I'm not. I'm still,
He's still reading.
reading the Godot documentation. Yeah, I know this is taking a while.
He's still fucking reading.
What do you expect? It's documentation.
I'm so fucking read.
Although this is probably
We've been
less.
reading for 5 episodes now.
Although this is
reading?
probably less documentation than some other game engines, but since this is a community-driven one,
Oh, gosh.
so. But yeah,
But
Anyway, I found a way to give myself a trillion lunar coins again, so...
fun.
yeah,
Yeah.
lovely.
It's not the way you do it, however you do that.
Somehow. Contact reporting. By default, rigid bodies do not keep track of contacts, because this can require a huge amount of memory. If many bodies are in the same scene, to enable contact reporting, set the max contacts reported property to a non-zero value. The contacts can then be obtained via physics of direct body state 2D get contact count and related functions. Contact monitoring via signals can be enabled via the contact monitor property. See rigid body 2D for the list of available signals. Character body 2D. Character body 2D bodies detect collisions with other bodies, but are not affected by physics properties like gravity or friction. Instead, they can be controlled by the user via code. The physics engine will not move a character body. When moving a character body, you should not set its position directly. Instead, use the move and collide or move and collide and move and slide methods. These methods move the body along a given vector, and it will instantly stop if a collision is detected with another body. After the body has collided, any collision response must be coded manually. Character collision response. After a collision, you may want the body to bounce, to slide along a wall, or to alter the properties of the object it hit. The way you handle collision response depends on which method you use to move the character body 2D. Move and collide. When using move and collide, the function returns a kinematic collision 2D object which contains information about the collision and the colliding body. You can use this information to determine the response. For example, if you want to find the point in space where the collision occurred, or to bounce off the colliding object. Move and slide. Sliding is a common collision response. Imagine a player moving along walls in a top-down game or running up and down slopes in a platforming. While it's possible to code this response yourself after using move and collide, and move and slide provides a convenient way to implement sliding movement without writing much code. Warning: move and slide automatically includes the time step in its calculation. You should not multiply the velocity vector by delta. This does not apply to gravity, as it is an acceleration and is time dependent, and needs to be sealed by delta. For example, use the following code to make a character that can walk along the ground, including slopes and jump when standing on the ground. See Kinematic Character 2D for more details on using move and slide, including a demo project with detailed code. Using Jolt Physics. Introduction. The Jolt Physics engine was used as an alternative to the existing Godot physics engine.
You good?
No. Physics and engine in 4.4. Jolt is developed by Gerrit Rowe with a focus on games and VR applications. Previously, it was available as an extension, but is now built into Godot. By default, new projects will use it as the physics engine. Oh, shut up. The existing extension is now considered in maintenance mode. That means bug fixes will be merged and will be kept compatible with new versions of Godot until the built-in module has feature parity with the extension. The only thing missing at this point is related joints, which you can read about on this page. The extension can be found here on GitHub and in Godot's asset library. To change the 3D physics engine to be Jolt Physics, set project settings Physics 3D Physics Engine to Jolt Physics. Oh, so this is a 3D engine thing? That means I can skip it.
Amazing.
Because I don't need that shit.
I don't need this shit.
I don't need 3D shit.
What is this shit?
Using rigid body. What is a rigid body? A rigid body is one that is directly controlled by the physics engine in order to simulate the behavior of physical objects. In order to define the shape of the body, it must have one or more shaped 3D objects assigned. Note that the setting the position of these shapes will affect the body's center of mass. How to control a rigid body. A rigid body's behavior can be altered by setting its properties, such as mass and weight. A physics material needs to be added to the rigid body to adjust its friction and bounce, and set if it's absorbent and or rough. These properties can be set in the inspector or via code. See Rigid Body 3D and Physics Material for the full list of properties and their effects. There are several ways to control a rigid body's movement depending on your desired applications. If you only need to place a rigid body once, for example to set its initial location, you can use the methods provided by the Node 3D node, such as set global transform or look at. However, these methods cannot be called every frame, or the physics engine will not be able to correctly simulate the body state. As an example, consider a rigid body that you want to rotate so that it points towards another object. A common mistake when implementing this kind of behavior is to use look at every frame, which breaks the physics simulation. Below will demonstrate how to implement this correctly. The fact that you can't use set global transform or look at methods doesn't mean that you can't have full control of a rigid body. Instead, you control it by using the integrate forces callback. In this method, you can add forces, apply impulses, or set the velocity in order to achieve any movement you desire. The look at method. As described above, using the Node 3D's look-at method can be used each frame to follow a target. Here's a custom look-at method called look-follow that will work with rigid bodies.
So these have been all your streams reading instructions.
Well, the first one I was setting up shit and fucking around, but so far, pretty much, yeah. There was one where I, for a good portion of it, just messed around in the GD code. In the GD code learning thing.
Geometry Dash?
No, Godot.
Yeah.
But yeah, for the most part, it's just been reading.
Amazing.
I've been skipping as much as I can. This method uses the rigid body's angular velocity property to rotate the body. The axis to rotate around is given by the cross product between the current forward direction and the direction one wants to look in. The clamp is a single method used to prevent the amount of rotation from going past the direction, which is wanted to be looked in, as the total amount of rotation needed is given by the arc cosine, of the dot product. This method can be used with the axis lock angular star as well. If more precise control is needed, solutions such as ones relying on quaternion may be required, as discussed in using 3D transforms. Using Area 2D. Introduction. Godot offers a number of collision objects to provide both collision detection and response. Trying to decide which one to use for your project can be confusing. You can avoid problems and simplify the development if you understand how each of them works and what their pros and cons are. In this tutorial, we'll look at the Area 2D node and show some examples of how it can be used. Note, this document assumes you're familiar with Godot's various physics bodies. Please read Physics Introduction first. What is an area? An area 2D defines a region of 2D space. In this space, you can detect other collision object 2D nodes overlapping, entering, and exiting. Areas also allow for overriding local physics properties. We'll explore each of these functions below. Area properties. Areas have many properties you can use to customize their behavior. The gravity, linear damp, and angular damp sections are used to configure the area's physics override behavior. We'll look at how to use those in area influence section below. Monitoring and monitorable are used to enable and disable the area. The audio bus section allows you to override audio in the area. For example, to apply an audio effect when the player moves through. Note that Area 2D extends collisions object 2D, so it also provides properties inherited from that class. The collision section of collision object 2D is where you configure the area's collision layers and masks. Ah, shit. I dropped the thing. Now I have to find a thing in a hard to reach place.
I dropped my balls.
Ew, what?
Now, how did you do that?
Note that Area 2D extends Collision 2D, so it also provides properties inherited from that class. The collision section of Collision Object 2D is where you configure that area's collision layers and masks. What?
I accidentally gave an equipment drone a recycler.
I died of death.
Perhaps the most common use of Area 2D nodes is for contact and overlap detection, when you need to know that two objects have touched but don't need physical collision. You can use an area to notify you of the contact. For example, let's say we're making a coin for the player to pick up. The coin is not a solid object. The player can't stand on it or push it. We just want it to disappear when the player touches it. Here's the node setup for the coin. To detect the overlap, we'll connect the appropriate signal of the Area 2D, which signal to use depends on the player's node type. If the player is another area, use area entered. However, let's assume our player is a character body 2D and therefore a collision object 2D type. So we'll connect the body entered signal. If you're not familiar with using signals, see using signals for an introduction. Now our player can collect the coins. Some other usage examples. Areas are great for bullets and other projectiles that hit and deal damage, but don't need any other physics such as bouncing. Use a circular area around an enemy to define its detect radius. When the player is outside the area, the enemy can't see it. Security cameras. In a large level with multiple cameras, attach areas to each camera and activate them when the player enters. See your first 2D game for an example of using Area 2D in a game. Area influence. The second major use for area nodes is to alter physics. By default, the area won't do this, but you can enable this with the space override property. When areas overlap, they are processed in priority order. Higher priority areas are processed first. There are 4 options for override. Combine. The area adds its values to what has been calculated so far. Replace. The area replaces physics properties, and lower priority areas are ignored. Combine. Replace. The area adds its gravity damping values to whatever has been calculated so far in priority order, ignoring any lower priority areas. Replace or combine. Replace, combine. The area replaces any gravity damping calculated so far, but keeps calculating the rest of the areas. Using these properties, you can create very complex behavior with multiple overlapping areas. The physics properties can be overridden here. Can be overridden are gravity. Gravity's strength is inside the area. Gravity direction. This vector does not need to be normalized. Linear damp has how quickly objects stop moving. Linear velocity, lost per second. Angular damp, how quickly objects stop spinning. Angular velocity, lost per second. Point gravity. The gravity point property allows you to create an attractor gravity, and the area will be calculated towards a point, given by the point center property. Values are relative to the area 2D, so for example, using 0, 0 will attract objects to the center of the area. Examples. The example project attached below has 3 areas demonstrating physics override. Point gravity, linear damp, reverse gravity. Using character body 2D or 3D. Introduction. Godot offers several collision objects to provide both collision detection and response. Trying to decide which one to use for your project can be confusing. You can avoid problems and simplify development if you understand how each of them works and what their pros and cons are. In this tutorial, we'll look at the character body 2D node and show some examples of how to use it. Note, while this document uses character body 2D in its examples, the same concept apply in 3D as well. What? You made a noise. What?
Never mind, don't worry about it.
Oh, okay. What is a character body? Character body 2D is for implementing bodies that are controlled via code. Character bodies detect collisions with other bodies when moving, but are not affected by engine physics properties like gravity or friction. While this means that you have to write some code to create their behavior, it also means you have more precise control over how they move and react. Note, this document assumes you're familiar with Godot's various physics bodies. Please read Physics Introduction first for an overview of the physics options. Tip: a character body 2D can be affected by gravity and other forces, but you must calculate the movement in code. The physics engine will not move a character body 2D. Movement and collision. When moving a character body 2D, you should not set its position property directly. Instead, you use the move and collide or move and slide methods. These methods move the body along a given vector and detect collisions. Warning: you should handle physics body movements in the physics process callback. The 2 movement methods serve different purposes, and later in this tutorial you'll see examples of how they work. Move and collide. This method takes one required parameter, a vector 2 indicating the body's relative movement. Typically, this is your velocity vector multiplied by the frame time step, delta. If the engine detects a collision anywhere along this vector, the body will immediately stop moving. If this happens, the method will return a kinematic collision 2D object. Kinematic collision 2D is an object containing a delta about the collision and the colliding object. Using this data, you can calculate your collision response. Move and collide. It is most useful when you're using when you just want to move the body and detect collision, but don't need any automatic collision response. For example, if you need a bullet that ricochets off a wall, you can directly change the angle of the velocity when you detect a collision. See below for an example. Move and slide. The move and slide method is intended to simplify the collision response in the common case where you want one body to slide along the other. It is especially useful in the platformers or top-down games, for example. When calling move and slide, the function uses a number of node properties to calculate its slide behavior. These properties can be found in the inspector or set in code. Velocity, default value, vector 2, 0, 0. This property represents the body's velocity velocity vector in pixels per second. Move and slide will modify this value automatically when colliding. Motion mode, default value, motion mode grounded. This property is typically used to distinguish between side scrolling and top-down movement. When using the default value, you can use the is on floor, is on wall, and is on ceiling methods to detect what type of surface the body is in contact with, and the body will interact with slopes when using motion mode floating. All collisions will be considered walls. Up direction, default value, vector 2, 0, negative 1. This property allows you to define what surfaces the engine should consider being the floor. Its value lets you use the is on floor, is on wall, is on ceiling methods to detect what type of surface the body is in contact with. The default value means that the top side of the horizontal surfaces will be considered ground. Floor stop on slope, default value true. This parameter prevents a body from sliding down slopes when standing still. Wall minimum slide angle, default value 0.261799, in radians equivalent to 15 degrees. This is the minimum angle where the body is allowed to slide when it hits a slope. Floor maximum angle, default value 0.785398, in radians equivalent to 45 degrees. The parameter is the maximum angle before a surface is no longer considered a floor. There are many other properties that can be used to modify the body's behavior under specific circumstances. See the Character Body 2D docs for full details. Detecting collisions. When using move and collide, the function returns a kinematic collision 2D directly, and you can use this in your code. When using move and slide, it's possible to have multiple collisions occur, as the slide response is calculated. To process these collisions, use getSlideCollisionCount and getSlideCollision. 1 second. Note getSlideCollisionCount only counts times the body has collided and changed direction. See kinematic collision 2D for details on what collision data is returned. Yeah.
Whenever you get a chance, you can put all your stuff on a shelf downstairs.
Okay.
And then you can hopefully use your department in that room.
Which movement method to use? A common question from new Godot users is, how do you decide which movement function to use? Often the response is to use move and slide because it seems simpler, but this is not necessarily the case. One way to think of it is that move and slide is a special case, and move and collide is more general. For example, the following two code snippets result in the same collision response. Anything you do with move and slide can also be done with move and collide, but it might take a little more code. However, as we'll see in the examples below, there are cases where move and slide doesn't provide the response you want. In the example above, move and slide automatically alters the velocity variable. This is because when the character collides with the environment, the function recalculates the speed internally to reflect the slowdown. For example, if your character fell on the floor, you don't want it to accumulate vertical speed due to the effect of gravity. Instead, you want its vertical speed to reset to 0. Move and slide may also recalculate the kinematic body's velocity several times in a loop as to produce a smooth motion. It moves the character and collides up to 5 times by default. At the end of the process, the character's new velocity is available for use on the next frame. Examples. To see these examples in action, download the sample project. I think I'm fine. Next, raycasting. Introduction. One of the most common tasks in game development is casting a ray or custom shaped object and checking what it hits. This enables complex behavior, AI, etc. to take place. This tutorial will explain how to do this in 2D and 3D. Godot stores all low-level game information in servers, while the scene is only affronted. As such, raycasting is generally a lower level task. For simple raycast, nodes like raycast 3D and raycast 2D will work as they return every frame what the result of a raycast is. Many times though, raycasting needs to be a more interactive process, so a way to do this is to do this by code must exist. Space. In the physics world, Godot stores all the low-level collision and space information in a space. The current 2D space for 2D physics can be obtained by accessing canvas item getWorld 2D space. For 3D, it's node 3D getWorld 3D space. The resulting space RID can be used in Physics Server 3D and Physics Server 2D, respectively, for 3D and 2D. Accessing space. Godot Physics. Oh, there goes Jesse. Godot Physics runs by default in the same threads as game logic, but may be set to run on a separate thread to work more efficiently. Due to this, the only time accessing space is safe is during the node physics process callback. Accessing it from outside this function may result in an error due to space being locked. To perform queries into physics space, the physics direct space state 2D and physics direct space state 3D must be used. Use the following code in 2D, or more directly, and in 3D. Raycast query. For performing a 2D raycast query, the method physics direct space state 2D intersect ray may be used. For example, the result is a dictionary. If the ray didn't hit anything, the dictionary will be accepted. If it did hit something, it will contain collision information. The result dictionary, when a collision occurs, contains the following data. The data is similar in 3D space using vector 3 coordinates. Note that to enable collisions with area 3D, the Boolean parameter collide with areas must be set to true. Collision exceptions. A common use case for raycasting is to enable a character to gather data about the world around it. One problem with this is that the same character has a collider, so the ray will only detect its parent colliders, as shown in the following image. To avoid self-intersection, the intersect ray parameters object can take an array of exceptions via its exclude property. This is an example of how to use it from a character body 2D or any other collision object node. The exceptions array can contain objects or RIDs. Collision mask. While the exception method works fine for excluding the parent body, it becomes very inconvenient if you need a large and/or dynamic list of exceptions. In this case, it's much more convenient to use the collision layer or mask system. The intersection ray parameters object can also be supplied a collision mask. For example, to use the same mask as the parent body, use the collision mask member variable. The array of exceptions can be supplied as the last argument as well. See code example for details on how to set the collision mask. 3D casting from screen. Casting a ray from screen to 3D physics space is useful for object picking. There is not much need to do this because collision object 3D has an input event signal that will let you know when it was clicked. But in case there is any desire to do it manually, here's how. To cast a ray from the screen, you need a camera 3D node. A camera 3D can be in two projection modes, a perspective and orthogonal. Because of this, both a ray origin and direction must be obtained. This is because origin changes in orthogonal mode, while normal changes in perspective mode. To obtain it using a camera, the following code can be used. Remember that during input the space may be locked, so in practice this query should be run in physics process. Ragdoll system. Introduction. Godot supports ragdoll physics. Ragdolls rely on physics simulation to create realistic procedural animation. They are used for death animations in many games. In this tutorial, we will be using the Platformer 3D demo to set up Ragdoll. I don't think I'm going to be using Ragdoll, so I can skip this. Kinematic Character 2D. Introduction. Yes, the name sounds strange. Kinematic character. What is that? The reason for the name is that when physics engines came out, they were called dynamics engines because they dealt mainly with collision responses. Many attempts were made to create a character controller using the dynamics engines, but it wasn't as easy as it seemed. Godot has one of the best implementations of dynamic character controller you can find, as it can be seen in the 2D platformer demo. But using it requires a considerable level of skill and understanding of physics engines, or a lot of patience with trial and error. Some physics engines, such as Havoc, seem to swear by dynamic character controllers as the best option, while others, PhysX, would rather promote the kinematic one. So what is the difference? A dynamic character controller uses a rigid body with an infinite inertia tensor. It's a rigid body that can't rotate. Physics engines always let objects move and collide, then solve their collisions altogether. This makes dynamic character controllers able to interact with other physics objects seamlessly, as seen in the platformer demo. However, these interactions are not always predictable. Collisions can take more than one frame to be solved, so a few collisions may seem to be displaced a tiny bit. Those problems can be fixed but require a certain amount of skill. A kinematic character controller is assumed to always begin in a non-colliding state and will always move to a non-colliding state. If it starts in a colliding state, it will try to free itself like rigid bodies do, but this is the exception, not the rule. This makes their control in motion a lot more predictable and easier to program. However, as a downside, they can't directly interact with other physics objects, unless done by hand in code. This short tutorial focuses on kinematic character controller, uses the old school way of handling collisions, which is not necessarily simpler under the hood, but well hidden and presented as an API. Physics process. To manage the logic of a kinematic body or character, it is always advised to use physics process, because it's called before physics step and its execution is in sync with physics server. Also, it is called the same amount of time per second always. This makes physics and motion calculation work in a more predictable way than using regular process, which might have spikes or lose precision if the frame rate is too high or too low. Scene setup. To have something to test, here's the scene from the tilemap tutorial. No need. Moving the kinematic character. Okay. Using soft body 3D, unnecessary. Collision shapes 2D. This guide explains the types of collision shapes available in 2D in Godot, using an image converted to a polygon as a collision shape. Performance considerations regarding 2D collisions. Godot provides many kinds of collision shapes with different performance and accuracy trade-offs. You can define the shape of a physics body 2D by adding one or more collision shape 2Ds or collision polygon 2Ds as direct child nodes. Indirect child nodes, i.e. children of child nodes, will be ignored and won't be used as collision shapes. Also note that you must add a shape 2D resource to collision shape nodes in the inspector doc. Note, when you add multiple collision shapes to a single physics body 2D, you don't have to worry about them overlapping. They won't collide with each other. Primitive collision shapes. Godot provides the following primitive collision shape types: rectangle shape 2D, circular shape 2D, capsule shape 2D, segment shape 2D, separation ray shape 2D, designed for characters, world boundary shape 2D, infinite plane. You can present the collision of most smaller objects using one or more primitive shapes. However, for more complex objects such as a large ship or a whole level, you may need convex or concave shapes instead. More on that below. We recommend favoring primitive shapes for dynamic shapes such as rigid bodies and character bodies, as their behavior is more reliable. They often provide better performance as well. Convex collision shapes. Godot currently doesn't offer a built-in way to create 2D convex collision shapes. This section is mainly here for reference purposes. Convex collision shapes are a compromise between primitive collision shapes and concave collision shapes. They can represent shapes of any complexity, but with an important caveat. As their name implies, an individual shape can only represent a convex shape. For instance, what the fuck? No. For instance, a pyramid is convex, but a hollow box is concave. To define a concave object with a single collision shape, you need to use a concave collision shape. Depending on the object's complexity, you may get better performance by using multiple convex shapes instead of a concave collision shape. Godot lets you use convex decomposition to create convex shapes that roughly match a hollow object. Note this performance advantage no longer applies after a certain amount of convex shapes. For large and complex objects, such as a whole level, we recommend using concave shapes instead. Concave or tri-mesh collision shapes. Concave collision shapes, also called tri-mesh collision shapes, can take any form, from a single triangle to thousands of triangles. Concave shapes are the slowest option, but are also the most accurate in Godot. You can only use concave shapes within static bodies. They will not work with character bodies or rigid bodies unless the rigid bodies mode is static. Note, even though concave shape offers the most accurate collision, contact reporting can be less precise than primitive shapes. When not using tile maps for level design, concave shapes are the best approach for levels collision. You can configure the collision polygon 2D nodes build mode in the inspector. If it is set to solids, the default collisions will include the polygon and its contained area. If it is set to the segments collisions will only include the polygon edges. You can generate a concave collision shape from the editor by selecting a Sprite 2D and using the Sprite 2D menu at the top of the 2D viewport. The Sprite 2D menu dropdown exposes an option called Create Collision Polygon 2D Sibling. Once you click it, it displays a menu with 3 settings. Simplifications, higher values, will result in a less detailed shape, which improves performance at the cost of accuracy. Shrink pixels, higher values will shrink the generated collision polygon relative to the sprite's edges. Grow pixels, higher values will grow the generated collision polygon relative to the sprite's edges. Note that setting grow and shrink to equal values may yield different results than leaving both of them on 0. Note, if you have an image with many small details, it's recommended to create a simplified version and use it to generate the collision polygon. This can result in better performance and game feel, since the player won't be blocked by small decorative details. To use a separate image for collision polygon generation, create another Sprite 2D, generate a collision polygon sibling from it, then remove the Sprite 2D node. This way, you can exclude small details from the generated collision. Performance caveats. You aren't limited to a single collision shape per physics body. Still, we recommend keeping the number of shapes as low as possible to improve performance, especially for dynamic objects like rigid bodies and character bodies. On top of that, avoid translating, rotating, or scaling collision shapes to benefit from the physics engine's internal optimizations. When using a single non-transform collision shape in a static body, the engine's broad phase algorithm can discard inactive physics bodies. The narrow phase will then only have to take into account the physics body's shapes if a static body has many collision shapes. The broad phase will fail. The narrow phase, which is slower, must then perform a collision check against each shape. If you run into performance issues, you may have to make trade-offs in terms of accuracy. Most games out there don't have a 100% accurate collision. They find creative ways to hide it or otherwise make it unnoticeable during normal gameplay. Collision Shapes 3D. This guide explains the type of collision shapes available in 3D in Godot, using a convex or concave mesh as a collision shape, performance considerations regarding 3D collisions. Godot provides many kinds of collision shapes with different performance and accuracy trade-offs. You can define the shape of physics body 3D by adding one or more collision shape 3Ds as direct child nodes. Indirect child nodes, i.e. children of child nodes, will be ignored and won't be used as collision shapes. Also note that you must add a shape 3D resource to collision shape nodes in the inspector dock. Note, when you add multiple collision shapes to a single physics body, you don't have to worry about them overlapping. They won't collide with each other. Primitive collision shapes. Godot provides the following primitive collision shapes. Collision shape types: box shape 3D, sphere shape 3D, capsule shape 3D, cylinder shape 3D. You can repeat the collision of most smaller objects using one or more primitive shapes. However, for more complex objects, such as a larger ship or whole level, you may need convex or concave shapes instead. More on that below. We recommend favoring primitive shapes for dynamic objects such as rigid bodies and character bodies, as behavior is the most reliable. They often provide more performance as well. Convex collision shapes. Convex collision shapes are a compromise between primitive collision shapes and concave collision shapes. They can represent shapes of any complexity, but with an important caveat. As their name implies, an individual shape can only represent a convex shape. For instance, a pyramid is convex, but a hollow box is concave. To define a concave box with a single collision type, you need to use a concave collision shape. Depending on the object's complexity, you may get performance by using multiple convex shapes instead of a concave collision shape. Godot lets you use convex decomposition to generate convex shapes that roughly match your hollow object. Note, this performance advantage no longer applies after a certain amount of convex shapes. For large and complex objects such as a whole level, we recommend using concave shapes instead. You can generate one or several convex collision shapes from the editor by selecting a Mesh Instance 3D and using the Mesh menu at the top of the 3D viewport. The editor exposes two generation modes. Create single convex collision sibling uses the quick kill algorithm. It creates one collision shape node with an automatically generated convex collision shape. Since it only generates a single shape, it provides good performance and is ideal for small objects. Create multiple convex collision siblings uses the VHACD algorithm. It creates several collision shape nodes, each with a convex shape. Since it generates multiple shapes, it is more accurate for concave objects at the cost of performance. For objects with medium complexity, it will likely be faster than using a single concave collision shape. Concave or tri-mesh collision shapes. Concave collision shapes, also called tri-mesh collision shapes, can take any form, from a few triangles to thousands of triangles. Concave shapes are the slowest option, but are the most accurate in Godot. You can only use concave shapes within static bodies. They will not work with character bodies or rigid bodies unless the rigid bodies mode is static. Note, even though concave shapes offer the most accurate collision, contact reporting can be less precise than primitive shapes. When not using grid maps for level design, concave shapes are the best approach for a level's collision. That said, if your level has small details, you may want to exclude those from collision for performance in game feel. To do so, you can build a simplified collision mesh in a 3D modeler and have Godot generate a collision shape for it automatically. More on that below. Note that unlike primitive and convex shapes, a concave collision shape doesn't have an actual volume. You can place objects both outside the shape as well as inside. You can generate concave collision shape. You can generate a concave collision shape from the editor by selecting a Mesh Instance 3D and using the Mesh menu at the top of the 3D viewport. The editor exposes two options. Create tri-mesh static body is a convenient option. It creates a static body containing a concave shape, matching the mesh's geometry. Create mesh collision sibling creates a collision sibling node with a concave shape matching the mesh's geometry. See important 3D scenes for information on how to export models for Godot and automatically generate collision shapes on import. Oh shit, I didn't need to read any of that. Large world coordinates. Large world coordinates are mainly useful in 3D projects. They're rarely required in 2D projects. Also, unlike 3D rendering, 2D rendering currently doesn't benefit from increased precision when large world coordinates are enabled. Alright, then I don't need to read this. Physics interpolation. Ah, shit. Quick start guide. Turn on physics interpolation. Project settings. Physics common. Physics interpolation. Make sure you move objects and run your game logic in physics process rather than process. This includes moving objects directly and indirectly. By example, moving a parent or using another mechanism to automatically move nodes. Be sure to call node reset physics interpolation on nodes after the first position or teleport them to prevent streaking. Temporarily try setting project settings physics common physics ticks per second to 10 to see the difference with and without interpolation. Introduction. Shit. Introduction, physics ticks and rendered frames. One key concept to understand in Godot is the distinction between physics ticks, sometimes referred to as iterations, or physics frames, and rendered frames. The physics proceeds at a fixed tick rate, set in project settings physics common physics ticks per second, which defaults to 60 ticks per second. However, the engine does not necessarily render at the same rate. Although many monitors refresh at 60 Hz cycles per second, many refresh at completely different frequencies. Example 75 Hz, 144 Hz, 240 Hz, or more. Even though a monitor may be able to show a new frame, example 60 frames per second, when running with VSync, the computer may be too slow for 60 and only reach the deadlines for 30 FPS, in which case the frames you see will change at 30 FPS, resulting in stuttering. But there is a problem here. What happens if the physics ticks do not coincide with frames? What happens if the physics tick rate is out of phase with the frame rate, or worse? What happens if the physics tick rate is lower than the rendered frame rate? This problem is easier to understand if we consider an extreme scenario. If you set the physics tick rate to 10 ticks per second in a simple game with a rendered frame rate of 60 FPS, if we plot a graph of the positions of the object against the rendered frames, you can see that the positions will appear to jump every 1/10 of a second, rather than giving a smooth motion. When the physics calculates a new position for a new object, it is not rendered in the position for just one frame, but for 6 frames. This jump can be seen in other combinations of tick or frame rates as glitches or jitter caused by this staircasing effect due to the discrepancy between physics tick time and rendered frame time. What can we do about frames and ticks being out of sync? Lock the tick frame rate together. Or lock the tick and frame rate together. The most obvious solution is to get rid of the problem by ensuring there is a physics tick that coincides with every frame. This used to be the approach on old consoles and fixed hardware computers. If you know that every player will be using the same hardware, you can ensure it is fast enough to calculate ticks at frames at example 50 frames per second. And you can be sure it will look great for everybody. However, modern games are often no longer made for fixed hardware. You will often be planning to release on desktop computers, mobiles, and more, all of which have huge variations in performance, as well as different monitor refresh rates. We will need to come up with a better way of dealing with the problem. Adapt the tick rate. Instead of designing the game at a fixed physics tick rate, we could allow the tick rate to scale according to the end user's hardware. We could, for example, use a fixed tick rate that works for the hardware, or even vary the duration of each physics tick to match a particular frame duration. This works, but there is a problem. Physics and game logic, which is often also run in the physics process, work best and most consistently when run at a fixed predetermined tick rate. If you attempt to run a racing game physics that has been designed for 60 ticks per second, at example 10 ticks per second, the physics will behave completely differently. Controls may be less responsive, collisions / trajectories can be completely different. You may test your game thoroughly at 60 TPS then find it breaks on end users' machines when it runs at a different tick rate. This can make quality assurance difficult, which can with hard to reproduce bugs, especially in AAA games where problems of this sort can be very costly. This can also be problematic for multiplayer games for competitive integrity, as running the game at certain tick rates may be more advantageous than others. Lock the tick rate, but use interpolation to smooth frames in between physics ticks. This has become one of the most popular approaches to deal with the problem, although it is optional and disabled by default. We have established that most desirable physics or game logic arrangement for consistency and predictability is a physics tick rate that is fixed at design time. The problem is the discrepancy between the physics position recorded and where we want a physics object to be shown on a frame to give smooth motion. The answer turns out to be simple, but can be a little hard to get your head around at first. Instead of keeping a track of just the current position of a physics object in the engine, we keep track of both the current position of the object and the previous position of the previous physics tick. Why do we need the previous position? In fact, the entire transform, including rotation and scaling, by using a little math magic. We can use interpolation to calculate what the transform of the object would be between those 2 points, in our ideal world of smooth, continuous movement. Linear interpolation. The simplest way to achieve this is linear interpolation or layering, which you may have used before. Let us consider only the position and the situation where we know that the previous physics tick x coordinate was 10 units and the current physics tick x coordinate is 30 units. Note, although the maths is explained here, you do not have to worry about the details, as the step will be performed for you under the hood. Godot may use more complex forms of interpolation, but linear interpolation is the easiest in terms of explanation. The physics interpolation fraction. If our physics ticks are happening 10 times per second, this example, what happens if our rendered frame takes place at time 0.12 seconds? We can do some math to figure out where the object would be to obtain a smooth motion between the 2 ticks. First of all, we have to calculate how far through the physics tick we want the object to be. If the last physics tick took place at 0.1 seconds, we are 0.2 seconds, 0.12 to 0.1, through a tick that we know will take 0.1 seconds, 10 ticks per second. The fraction through the tick is thus. This is called the physics interpolation fraction and is handily calculated for you by Godot. It can be retrieved on any frame by calling engine get physics interpolation fraction. Calculating the interpolated position. Once we have the interpolation fraction, we can insert it into a standard linear interpolation equation. The x-coordinate would be thus. So substituting x prev as 10 and x cur as 30. Let's break that down. We know the x starts from the coordinate on the previous tick, x previous, which is 10 units. We know that after the full tick, the difference between the current tick and the previous tick will have been added x current minus x previous, which is 20 units. The only thing we have to vary is the proportion of the difference we add, according to how far we are through the physics tick. Notice, although this example interpolates the position, the same thing can be done with the rotation and scale of objects. It is not necessary to know the details, as Godot will do all this for you. Smooth transition between physics ticks. Putting all this together shows that it should be possible to have a nice smooth estimation of the transform of objects between the current and previous physics tick. But wait, you may have noticed something. If we are interpolating between the current and previous tick, we are not estimating the position of the object now. We are estimating the position of the object in the past. To be exact, we are estimating the position of the object between 1 and 2 ticks into the past. In the past, what does this mean? This scheme does work, but it does mean we are effectively introducing a delay between what we see on the screen and where the objects should be. In practice, most people won't notice this delay, or rather, it is typically not objectionable. There are already significant delays involved in games. We just don't typically notice them. The most significant effect is there can be a slight delay to input, which can be a factor in fast twitch games. In some of these fast input situations, you may wish to turn off physics interpolation and use a different scheme, or use a high tick rate which mitigates these delays. Why look into the past? Why not predict the future? There is an alternative to this scheme, which is, instead of interpolating between the previous and current tick, we use maths to interpolate into the future. We try to predict where the object will be rather than show it where it was. This can be done and may be offered as an option in future, but there are some significant downsides. The prediction may not be correct, especially when an object collides with another object during the physics tick. Where a prediction was incorrect, the object may extrapolate it into an impossible position, like inside a wall. Providing the movement speed is slow, these incorrect predictions may not be too much of a problem. When a prediction was incorrect, the object may have to jump to or snap back into the corrected path. This can be visually jarring. Fixed time step interpolation. In Godot, this whole system is referred to as physics interpolation, but you may also hear it referred to as fixed time step interpolation, as it is interpolating between objects moved with a fixed time step, physics ticks per second. In some ways, the second term is more accurate, because it can also be used to interpolate objects that are not driven by physics. Tip: although physics interpolation is usually a good choice, there are exceptions where you may choose not to use Godot's built-in physics interpolation or use it in a limited fashion. An example category is internet multiplayer games. Multiplayer games often receive tick or timing-based information from other players or a server, and these may not coincide with local physics ticks. So a custom interpolation technique can often be a better fit. Oh, fuck. Using physics interpolation. How do we incorporate physics interpolation into a Godot game? Are there any caveats? We have tried to make the system as easy to use as possible, and many existing games will work with few changes. That said, there are some situations which require special treatment, and these will be described. Turn on physics interpolation settings. The first step is to turn on physics interpolation in project settings, common physics interpolation. You can now run your game. It is likely that nothing looks hugely different, particularly if you're running physics at 60 ticks per second or a multiple of it. However, quite a bit more is happening behind the scenes. Tip: to convert an existing frame to use interpolation, it is highly recommended that you temporarily set project settings, common physics tick per second, to a low value such as 10, which will make interpolation problems more obvious. Move almost all game logic from process to physics process. The most fundamental requirement for physics interpolation, which you may be doing already, is that you should be moving and performing game logic on your objects within physics process, which runs at a physics tick rather than the process, which runs at a rendered frame. This means your physics script should typically be doing the bulk of their processing within physics process, including responding to input and AI. Setting the transform of objects only within physics ticks allows the automatic interpolation to deal with the transform between physics ticks, and ensures the game will run the same whether the machine it is run on. As a bonus, this also reduces CPU usage if the game is rendered at high FPS, since AI logic, for example, will no longer run at every rendered frame. Note: if you attempt to set the transform of interpolated objects outside of the physics tick, the calculations for the interpolated position will be incorrect, and you will get jitter. This jitter may be invisible on your machine, but will occur for some players. For this reason, setting the transform of interpolated objects should be avoided outside of the physics tick. Godot will attempt to produce warnings in the editor if this case is detected. Tip: this is only a soft rule. There are some occasions where you might want to teleport objects outside of the physics tick, for instance when starting a level or respawning objects. Still, in general, you should be applying transforms from the physics tick. Ensure that all indirect movement happens during the physics tick. Consider that in Godot, nodes can be moved not just directly in your own scripts, but also by automatic methods such as tweening, animation, and navigation. All these methods can All these methods should also have their timing set to operate on the physics tick rather than each frame idle. If you are using them to move objects, these methods can also be used to control properties that are not interpolated. Note, also consider that nodes can be removed not just by moving themselves, but also by moving parent nodes in the scene tree. The movement of parents should therefore also only occur during physics ticks. Choose a physics tick rate. When using physics interpolation, the rendering is decoupled from physics, and you can choose any value that makes sense for your game. You are no longer limited to values that are multiples of the user's monitor refresh rate. For stutter-free gameplay, if the target FPS is reached. As a rough guide, low tick rate. You can always change the tick rate as you develop. It is as simple as changing the project settings. Call reset physics interpolation when teleporting objects. Most of the time, interpolation is not what you want between two physics ticks. However, there is one situation in which it may not be what you want. May not be what you want. That is when you're initially placing objects or moving them to a new location. Here, you don't want a smooth motion between where the object was, example, the origin and the initial position. You want an instantaneous move. The solution is to call the node reset physics interpolation function, what this function does under the hood is set the internally stored previous transform of the object to be equal to the current transform. This ensures that when interpolating between these two equal transforms, there will be no movement. Even if you forget to call this, it will usually not be a problem in most situations, especially at high tick rates. This is something you can easily leave to the polishing phase of your game. The worst that you will happen to see is a streaking motion for a frame or so when you move them. You'll know when you need it. There are actually two ways to use reset physics interpolation. Standing start, example player, set the initial transform, call reset physics interpolation. The previous and current transforms will be identical, resulting in no initial movement. Moving start, example bullet, set the initial transform, call reset physics interpolation. Immediately set the transform expected after the first tick of motion. The previous transform will be the starting position, and the current transform will act as though a tick of simulation has already taken place. This will immediately start moving the object instead of having a tick delay standing still. Important. Make sure you set the transform and call reset physics interpolation in the correct order as shown above. Otherwise, you will see unwanted streaking. Testing and debugging tips. Even if you intend to run physics at 60 TPS in order to thoroughly test your interpolation and get the smoothest gameplay, it is highly recommended to temporarily set the physics tick rate to a low value such as 10 TPS. The game may not work perfectly, but it should enable you to more easily see cases where you should be calling node reset physics interpolation, or where you should be using your own custom interpolation on example camera 3D once you have these cases fixed. You can set the physics tick rate back to the desired setting. The other great advantage to testing at a low tick rate is you can often notice other game systems that are synchronized to the physics tick and creating glitches which you may want to work around. Typical examples include setting animation blend values, which you may decide to set in process and interpolate manually. Note, in 2D, the position of visible collision shapes shown by the debug visible collision shapes option will take physics interpolation into account. By contrast, in 3D, the position of visible collision shapes will not take physics interpolation into account. This means the visible collision shapes can appear to move less smoothly and appear slightly in front of the object's visual representation when the object is moving. This is not a bug, but a consequence of how physics interpolation is implemented in 3D. Advanced physics interpolation. 2 left. This one is somewhat short. Although the previous instructions will give satisfactory results in a lot of games, in some cases you will want to go a stage further to get the best possible results and the smoothest possible experience. Exception to automatic physics interpolation. Even with physics interpolation active, there may be some local situations where you would benefit from disabling automatic interpolation for a node or branch of the scene tree, and have the finer control of performing interpolation manually. This is possible using the node physics interpolation mode property, which is present in all nodes. If you, for example, turn off interpolation for a node, the children will recursively use but will also be affected as they default to inheriting the parent setting. This means you can easily disable interpolation for an entire subscene. The most common situation where you may want to perform your own interpolation is cameras. Cameras. In many cases, a camera 3D can use automatic interpolation just like any other node. However, for best results, especially at low physics tick rates, it is recommended that you take a manual approach to camera interpolation. Manual camera interpolation. Ensure the camera is using global coordinate space. The first step when performing manual camera interpolation is to make sure the camera 3D transform is specified in global space rather than inheriting the transform of a moving parent. This is because feedback can occur between the movement of a parent node of a camera 3D and the movement of the camera node itself, which can mess up the interpolation. There are two ways of doing this. One, move the camera 3D so it is independent on its own branch, rather than being a child of a moving object. Call node 3D top level and set this to true, which will make the camera ignore the transform of its parent. A typical example of a custom approach is to use the look at function in the camera 3D every frame in process to look at a target node, such as the player. But there's a problem. If we use the traditional get global transform on a camera 3D target node, this transform will only focus on the camera 3D on the target at the current physics tick. This is not what we want, as the camera will jump about on each physics tick as the target moves. Even though the camera may be updated each frame, this does not help give smooth motion if the target is only changing each physics tick. Get global transform interpolated. What we really want to focus the camera on is not the position of the target on the physics tick, but the interpolated position, i.e. the position at which the target will be rendered. We can do this by using the node 3d.getGlobalTransform interpolated function. This acts exactly like getting node 3D global transform, but it gives you interpolated transform during a process call. Important, get global transform interpolated should only be used once or twice for special cases such as cameras. It should not be used for all over the place. It should not be used all over the place in your code, both for performance reasons and to give correct gameplay. Note, aside from exceptions like the camera, in most cases your game logic should be in physics process. In game logic, it should be called getGlobalTransform or getTransform, which will give the current physics transform in global or local space respectively, which is usually what you will want for gameplay code. Example, manual camera script. Here's an example of a simple fixed camera which follows an interpolated target. Mouse look. Mouse look is a very common way of controlling cameras, but there is a problem. Unlike keyboard input, which can be sampled periodically on the physics stick, mouse movement events can come in continuously. The camera will be expected to reach and follow the mouse movements on the next frame, rather than waiting until the next physics tick. In this situation, it can be better to disable physics interpolation for the camera node, using node physics interpolation mode, and directly apply the mouse input to the camera rotation rather than applying it to physics process. Sometimes, especially with cameras, you'll want to use a combination of interpolation and non-interpolation. A first-person camera may position the camera at a player location, perhaps using node 3D get global transform interpolated, but control the camera rotation from mouse look without interpolation. A third-person camera may similarly determine the look at target location of the camera using node 3D get global transform interpolated, but position the camera using the mouse without look without interpolation. There are many permutations of and variations of camera types, but it should be clear that in many cases, disabling automatic physics interpolation and handling this yourself can give a better result. Disabling interpolation on other nodes. Although cameras are the most common example, there are a number of cases when you may wish other nodes to control their own interpolation, or be non-interpolated. Consider, for example, a player in a top-view game whose rotation is controlled by mouse look. Disabling physics rotation allows the player rotation to match the mouse in real time. Multi-meshes. Although most visual nodes follow the single visual instance paradigm, multi-meshes can control several instances from the same node. Therefore, they may have some extra functions for controlling interpolation functionality on a per instance basis. You should explore these functions if you are using interpolated multi-meshes. Multi-mesh reset instance physics interpolation, multi-mesh set buffer interpolated. Full details are in the multi-mesh documentation. Okay. 2D and 3D physics interpolation. Generally, 2D and 3D physics interpolation work in very similar ways. However, there are a few differences which will be described here. Global versus local interpolation. In 3D, physics interpolation is performed independently on the global transform of each 3D instance. In 2D, by contrast, physics interpolation is performed on the local transform of each 2D instance. This has some implications. In 3D, it is easy to turn interpolation on and off at the level of each node via the physics interpolation mode property in the inspector, which can be set to on, off, or inherited. However, this means that in 3D, pivots that occur in the scene tree due to parent-child relationships can only be interpolated approximately over the physics tick. In most cases, this will not matter, but in some situations, the interpolation may look slightly wrong. In 2D, interpolated local transforms are passed down to children during rendering. This means that if a parent has physics interpolation mode set to on, but the child is set to off, the children will still be interpolated if the parent is moving. Only the child's local transform is uninterpolated. Controlling the on or off behavior of 2D nodes therefore requires a little more thought and planning. On the positive side, pivot behavior in the scene tree is perfectly preserved during interpolation in 2D, which gives super smooth behavior. Resetting physics interpolation. Whenever objects are moved to a completely new position and interpolation is not desired so as to prevent a streaking artifact, it is the responsibility of all users of the user to call reset physics interpolation. The good news is that in 2D, this is automatically done for you when nodes first enter the tree. This reduces boilerplate and reduces the effort required to get an existing project working. Note, if you move objects after adding to the scene tree, you will still need to call reset physics interpolation as with 3D. 2D particles, currently only CPU particles 2D are supported for physics interpolation in 2D. It is recommended to use a physics tick rate of at least 20 to 30 ticks per second to keep particles looking fluid. Particles 2D, GPU particles, are not yet interpolated, so for now it is recommended to convert to CPU particles 2D, but keep a backup of your particles 2D in case we get these working. Other, get global transform interpolated, is currently only available for the 3D. Multi-meshes are supported in both 2D and 3D. Physics interpolation in 2D implemented on the server side, which means it's affected on the physics bodies created using low-level servers. In contrast, physics interpolation in 3D is implemented on the scene side. This means it does not affect physics bodies created using servers. These must be interpolated manually instead. See the pull request description for the rationale on the design decision. Troubleshooting physics issues. When working with a physics engine, you may encounter unexpected results. While many of these issues can be resolved through configuration, some of them are the result of engine bugs. For known issues related to the physics engine, see open physics related issues on GitHub. Looking through closed issues can also help answer questions related to the physics engine behavior. Interesting. Objects are passing through each other at high speeds. This is known as tunneling, enabling continuous CD in the rigid body properties can sometimes resolve the issue. If this does not help, there are other solutions you can try. Make your static collision shapes thicker. For example, if you have a thin floor that the player can't get below in some way, you can make the collider thicker than the floor's visual representation. Modify your fast-moving object's collision shape depending on its movement speed. The faster the object moves, the larger the collision shape should extend outside of the object to ensure it can collide with thin walls more reliably. Increase physics tick per second in the advanced project settings. While this has other benefits such as more stable simulation and reduced input lag, this increases CPU utilization and may not be viable for mobile or web platforms. Multipliers of the default value of 60, such as 120, 180, or 240, should be preferred for a smoother appearance on most displays. Stacked objects are unstable and wobbly. Despite seeming like a simple problem, stable rigid body simulation with stacked objects is difficult to implement in a physics engine. This is caused by integrating forces going against each other. The more stacked objects are present, the stronger the forces will be against each other. This eventually causes the simulation to become wobbly, making the objects unable to rest on top of each other without moving. Increasing the physics simulation rate can help alleviate this issue. To do so, increase the physics ticks per second in the advanced project settings. Note that increases CPU utilization and may not be viable for mobile or web platforms. Multipliers of the default value of 60, such as, should be preferred for smooth appearance on most displays. In 3D, switching the physics engine from the default Godot physics to Jolt can also improve stability. See using Jolt physics for more information. Scaled physics bodies or collision shapes do not collide correctly. Godot does not currently support scaling of physics bodies or collision shapes. As a workaround, change the collision shapes extents instead of changing its scale. If you want the visual representation's scale to change as well, change the scale of the underlying visual representations, write 2D mesh instance 3D, and change the collision shape's extents separately. Make sure the collision shape is not a child of the visual representation in this case. Since resources are shared by default, you'll have to make the collision shape resource unique if you don't want the change to be applied to all nodes using the same collision shape resource in the scene. This can be done by calling a duplicate in the script on the collision shape resource before changing its size. Thin objects are wobbly when resting on the floor. This can be due to one of the two causes. The floor's collision shape is too thin, the rigid body's collision shape is too thin. In the first case, we can alleviate this. This can be alleviated by making the floor's collision shape thicker. For example, if you have a thin floor that the player can't get below in some way, you can make the collider thicker than the floor's visual representation. In the second case, this can usually only be resolved by increasing the physics simulation rate, as making the shape thicker would only cause a disconnect between the rigid body's visual representation and its collision. In both cases, increasing the physics simulation rate can also help alleviate this issue. To do so, increase physics ticks per second in the advanced project settings. Note that this increases CPU utilization and may not be available for mobile or web platforms. Cylinder collision shapes are unstable. Switching to physics engine from default Godot physics to Jolt should make cylinder collision shapes more reliable. See using Jolt physics for more information. During the transition from Bullet to Godot physics in Godot 4, cylinder collision shapes had to be re-implemented from scratch. However, cylinder collision shapes are one of the most difficult shapes to support, which is why many other physics engines don't provide any support for them. There are several known bugs with cylinder collision shapes currently. If you are sticking to Godot physics, we recommend using box or capsule collision shapes for characters for now. Boxes generally provide the best reliability, but have the downside of making the character take more space diagonally. Capsule collision shapes do not have this downside, but their shape can make precision platforming more difficult. Vehicle body simulation is unstable, especially at high speeds. When a physics body moves at a high speed, it travels at a large distance between each physics step. For instance, when using the 1 unit per 1 meter convention in 3D, vehicle moving at 360 kilometers per hour will travel 100 units per second. With the default physics simulation rate of 60 Hz, the vehicle moves by approximately 1.67 units each physics tick. This means that small objects may be ignored entirely by the physics vehicle due to tunneling, but also that the simulation has little data to work with in general at such a high speed. Fast-moving vehicles may benefit a lot from an increased physics simulation rate. To do so, increase physics. Collision results in bumps when an object moves across tiles. This is a known issue in the physics engine caused by the object bumping on a shape's edge, even though the edge is covered by another shape. This can occur in both 2D and 3D. The best way to work around this issue is to create a composite collider. This means that instead of individual tiles having their collision, you can create a single collision shape representing the collision for each group of tiles. Typically, you should split composite colliders on a per island basis, which means each group of touching tiles gets their own collider. Using a composite collider can also improve physics simulation performance in certain cases. However, since the composite collision shape is much more complex, this may not be a net performance win in all cases. Tip: in Godot 4.5 and later, creating a composite collider is automatically done when using a tile map layer node. The chunk size, 16 tiles on each axis by default, can be set using the physics quadrant size property in the tile map layer inspector. Larger values provide more reliable collision at the cost of slower updates when the tile map is changed. Frame rate drops when an object touches another object. This is likely due to one of the following uses of a collision shape that is too complex. Convex collision shapes should use a number of shapes as low as possible for performance reasons when relying on Godot's automatic generation. It's possible that you ended up with dozens, if not hundreds of shapes created for a single convex shape collision resource. In some cases, replacing a convex collider with a couple of primitive collision shapes, box, sphere, or capsule, can deliver better performance. This issue can also occur with static bodies that use very detailed tri-mesh concave collisions. In this case, we use simplified representation of the level geometry as a collider. Not only this will improve physics simulation performance significantly, but this can also improve stability by letting you perform small fixtures and crevices from being considered by the collision. Frame rate suddenly drops due to very low value beyond a certain amount of physics simulation. This occurs because the physics engine can't keep up with the expected simulation rate. In this case, the frame rate will start dropping, but the engine is only allowed to simulate a certain number of physics steps per rendered frame. This snowballs into a situation where frame rate keeps dropping until it reaches a very low frame rate, typically 1 to 2 FPS, and is called the physics spiral of death. To avoid this, you should check for situations in your project that can cause excessive number of physics simulations to occur at the same time, or with excessively complex collision shapes. If these situations cannot be avoided, you can increase the max physics steps per frame project setting and or reduce physics ticks per second to alleviate this. Physics simulation is unreliable when far away from the world origin. This is caused by floating point precision errors, which become more pronounced as the physics simulation occurs farther away from the world origin. This issue also affects rendering, which results in wobbly camera movement when far away from the world origin. See large world coordinates for more information. Yep. Don't need to worry about platform specific because we're only working with Windows, so we can just skip to plugins. Editor plugins. Do I need to read this? I don't know. I don't. I'm looking at the stream time here. We've been going for 4 hours and 40 minutes. I've been trying to think what time we should stop, because right now it's 6:52 for me. And I kind of want to end at 8, or sometime after 8. So I'll probably do that. I'll probably do that. Installing plugins. Godot features an editor plugin system with numerous plugins developed by the community. Plugins can extend the editor's functionality with new modes, additional docs, convenience features, and more. Finding plugins. The preferred way to find Godot plugins is to use the asset library. While it can be browsed online, it's more convenient to use it directly from the editor. To do so, click the Asset Library tab at the top of the editor. You can also find assets on code hosting websites such as GitHub. Note some repositories describe themselves as plugins, but may not actually be editor plugins. This is especially the case for scripts that are intended to be used in a running project. You don't need to enable such plugins to use them. Download them and extract the files in your project folder. One way to distinguish editor plugins from non-editor plugins is to look for a plugin CFG in the repository that hosts the plugin. If the repository contains a plugin.cfg file in the folder placed in the add-ons folder, then it is an editor plugin. Installing a plugin. To install a plugin, download it as a zip archive on the asset library. This can be done using the download button, either from the editor or using the web interface. On GitHub, if a plugin has tags versions declared, go to the release tag to window a stable release. This ensures you download a version that was declared to be stable by its author. On GitHub, if the plugin doesn't have any tags declared, use the download zip button to download a zip of the latest version. Extracting the zip archive and move the add-ons folder it contains into your project folder. If your project already contains an add-on folder, move the plugins add-ons folder into your project folder to merge the new folder contents with the existing one. Your file manager may ask you whether to write into the folder. Answer yes, no files will be overwritten in the process. Enabling a plugin. To enable the freshly installed plugin, open project settings at the top of the editor, then go then go the plugins tab. Then go to plugins tab. If the plugin was packaged correctly, you should see it in the list of plugins. Click on the enable checkbox to enable the plugin. You can use the plugin immediately after enabling it. There is no need to restart the editor. Likewise, disabling the plugin can be done without having to restart the editor. Making plugins. I don't need to worry about this. Making main screen plugins. Import plugins. Work in progress. Import plugins. Note, this tutorial assumes you already know how to make generic plugins. If in doubt, refer to making plugin page. Inspector plugins. The inspector doc allows you to create custom widgets to edit properties through plugins. This can be beneficial when working with custom data types and resources, although you can use the feature to change the inspector widget for built-in types. You can design custom controls for specific properties, entire objects, and even separate controls associated with particular data types. This guide explains how to use the editor inspector plugin and editor property classes to create a custom interface for integers, placing visual shader plugins, running the code in the editor. Running code in the editor. What is @tool? @tool is a powerful line of code that, when added at the top of your script, makes it execute in the editor. You can also decide what parts of the script execute in order, which in-game and which in both. You can use it for doing many things, but it is mostly useful in level design for visually presenting things that are hard to predict ourselves. Here are some use cases. If you have a cannon that shoots cannonballs affected by physics, gravity, you can draw the cannonballs directory in the editor, making level design a lot easier. If you have jump pads and with varying jump heights, you can draw the maximum jump height a player would reach if it jumped on one, also making level design easier. If your player doesn't use a sprite but draws itself using code, you can make that drawing code execute in the editor to see your player. Danger: scripts run inside the editor and let you access the scene tree of the currently edited scene. This is a powerful feature which also comes with caveats, as the editor does not include protections for potential misuse of @tool scripts. Be extremely cautious when manipulating the scene tree, especially via node queue free, as it can cause crashes if you free a node while the editor runs logic involving it. How to use @tool. To turn a script into a tool, add the @tool annotation at the top of your code. To check if you are currently in the editor, use engine is editor hint. For example, if you want to execute some code only in the editor, use. On the other hand, if you want to execute code only in-game, simply negate the same statement. Pieces of code that do not have either of the two conditions above will run both in editor and in-game. Here is how a process function might look for you. Important information. The general rule is that any other GD script that your tool script uses must also be a tool. The editor is not able to construct instances from GD script files without @tool, which means you cannot call methods or reference member variables from them otherwise. However, since static methods, constants, and enums can be used without creating an instance, it is possible to call them or reference them from a @tool script onto another non-tool scripts. One exception to this are static variables. If you try to read a static variable's value in a script that does not have @tool, it will always return null, but won't print a warning or error when doing so. The restriction does not apply to static methods, which can be called regardless of whether the target script is in tool mode. Extending a @tool script does not automatically make the extended script a tool. Omitting @tool from the extending script will disable behavior from the superclass. Therefore, the extending script should also specify the @tool annotation. Modifications in the editor are permanent with no undo or redo possible. For example, in the next section, when we move the script, the node will keep its rotation. Be careful to avoid making unwanted modifications. Consider setting up version control to avoid losing work in case you make a mistake. Debugging. While the debugger and breakpoints cannot be used directly with tool scripts, it is possible to launch a new instance of the editor and debug from there. To do this, navigate to Debug, Customize Run Instances, and specify Editor in main run arguments. See overview of debugging tools for more information. Additionally, you can use print statements to display the contents of variables instead. Try @tool out. Add a sprite 2D node to your scene. Set the texture to Godot icon, attach the open script, and change it to this. Save the script and return to the editor. You should now see your object rotate. If you run the game, it will also rotate. Warning, you may need to restart the editor. This is a known bug found in all Godot 4 versions. Note, if you don't see the changes, reload the scene, close it and open it again. Note, now let's choose which code runs when modify your process function looks like this. Save the script. Now the object will spin clockwise in the editor, but if you run the game, it will spin counterclockwise. Editing variables. Add and export a variable speed to the script. To update the speed and also reset the rotation angle, add a setter, set new speed, which is executed with the input from the inspector. Modify process to include the new rotation speed. Note, code from other nodes doesn't run in the editor. Your access to other nodes is limited. You can access the tree and nodes and their default properties, but you can't access the user variables. If you want to do so, other nodes have to run in the editor too. Get notified when resources change. Sometimes you want your tool to use a resource. However, when you change a property of that resource in the editor, the set method of your tool will not be called. To get around this problem, you will have to make your resource a tool and make it emit the change signal whenever a property is set. You then want to connect the signal when a new resource is set. Lastly, remember to disconnect the signal as the old resource being used and change somewhere else would cause unneeded updates. Reporting node configuration warnings. Godot uses a node configuration warning system to warn users about incorrectly configured nodes. When a node isn't configured correctly, a yellow warning sign appears next to the node's name in the scene dock. When you hover or click on the icon, a warning message pops up. You can use this feature in your scripts to help you and your team avoid mistakes when setting up scenes. When using node configuration warnings, when any value that should affect or remove the warning changes, you need to call update configuration warnings by default. The warning only updates when closing and reopening the scene. Running one-off scripts using editor script. Sometimes you need to run code just one time to automate a certain task that is not available in the editor outside of the box. Some examples might be use a playground for GD script or C# scripting without having to run a project. A print output is displayed in the editor output panel. Scale all light nodes in the currently edited scene. As you notice, your level ends up looking too dark or too bright after placing lights where desired. Replacing nodes that were copy-pasted with the scene instances to make them easier to modify later. This is available in Godot by extending editor script in a script. This provides a way to run individual scripts in the editor without having to create an editor plugin. To create an editor plugin, right-click a folder or empty space in the file system dock, then choose New Script. In the script create dialog, click the create tree icon to choose an object to extend from, or enter editor script directly in the field on the left, though note this is case sensitive. This will automatically select a script template that is suited for editor scripts with a run method already inserted. This run method is executed when you use any of the 4 approaches that can be used to run an editor script. Use file run at the top of the script editor with the editor script being the current tab. Press the keyboard shortcut Ctrl-Shift-X while the editor script is the current tab. This keyboard shortcut is only effective when focused on the script editor. Right-click the script in the file system dock and choose Run. Add a class name at the name at the top of the script. Bring up the command palette by pressing Ctrl-Shift-P and enter the class name to run it. The entry will be named according to the class name with automatic capitalization applied. The scripts that extend editor script must be @tool scripts to function. Note, editor scripts can only be run from the Godot script editor. If you are using an external editor, use one of the last 2 approaches to run the script. Note, C# editor scripts cannot be run from the script editor as it only supports GD script. Please refer to the above alternative approaches to run custom C# editor scripts. Keep in mind, C# tool scripts will only appear in the command palette when denoted by the global class attribute. Warning, editor scripts have no undo or redo functionality, so make sure to save your scene before running one if the script is designed to modify any data. To access nodes in the currently edited scene, use the editor interface get edited scene root method, which returns the root node of the currently edited scene. Here's an example that recursively gets all nodes in the currently edited scene and doubles the range of all OmniLight 3D nodes. In the above example, we also call editor script mark scene as unsaved after any modification that affects the scene template, the scene state. This allows the editor to display the scene as unsaved, i.e. with an asterisk next to the name. This way you also get a confirmation when trying to close the scene with unsaved changes. Tip: you can change the current edited scene at the top of the editor while the script view is open. This will affect the return value of the editor interface get edited scene root, so make sure you've selected the scene you intend to iterate upon before running the script. Instancing scenes. You can instantiate packed scenes normally and add them to the scene currently opened in the editor. By default, nodes or scenes added with node add child node are not visible in the scene tree doc and are not persisted to disk. If you wish the node or scene to be visible in the scene tree doc and persisted disk when saving the scene, you need to set the child node's owner property to the currently edited scene root. If you are using @tool, if you are using editor script. Warning, use @tool improperly can yield many errors. It is advised to first write the code how you want it and only then add the @tool annotation at the top. Also make sure to separate code when that runs in editor from code that runs in game. This way you can find bugs more easily. Yay! Next thing, rendering. I have no idea. Start and input the compositor. Yeah, I'll go through this. Overview of renders. See also the page gives an This page gives an overview of Godot renderers, focusing on the differences between their rendering features. For more technical details of the render, see internal rendering architecture. I wonder where that is. Introduction. Godot 4 includes 3 renderers. Forward Plus, the most advanced render, suited for desktop platforms only. Used by default on... I think I'm fine not going through this. Using viewports. Think of a viewport as a screen onto which the game is projected in order to see the game. Okay, I think we're fine. Multiple resolutions. Alright. We can just move on to scripting, I think. Scripting. This section covers programming languages and core features to code your games in Godot. Here you'll find information that is not already covered in more specific sections. For instance, to learn about inputs, we recommend you read Inputs. Programming languages. The section below each focus on a given programming language. Core features. And some features are specific to the game engine and are available in all supported languages. Whether you code in GDScript, C# or another language, the pages below will help you make the most of Godot. Alright, GDScript. Yeah, that checks out. Shit, wait. See also GDScript grammar if you're interested in writing a third-party tool that interacts with GDScript, such as a linter or formatter. GDScript reference. GDScript is a high-level... oh, fuck. This is a long-ass page. GDScript is a high-level object-oriented, imperative, and gradually typed programming language built for Godot. It uses an intent... You know what? I can just do this tomorrow. Scripting is easily going to be one of the longest parts, and I should really look at this. Yeah, this would take me a while to read through. Not to mention, that's decently long. That's long. That's actually kind of short. That's also kind of short. Decently long. Short. Somewhat long. So yeah, the scripting section would take forever to get through, and I don't think I can get through that in an hour. So I think I'll just